Yeah, we have a slide whiteboard.
Okay, good morning everyone. Welcome to day 2. So again, thanks to those online joining from whichever time zone you're in. Good morning, good afternoon, good evening. It's my fantastic, great pleasure this morning to be able to introduce Megan Reiter, who's going to tell us about the work they've been doing on the Carina image that we saw in July, the cosmic cliffs. So over to you, Megan.
Great, thank you. Is that a clicker? Okay, so first things first, can you hear me? I got the green button. Great. Thank you. So thank you very much for this great conference. Thank you for this great telescope. And I also want to say thank you to the ERO team who were kind enough to look at one of my favorite things and then immediately make the data available so that we could dive right in. So I will be talking about this image that we've seen a few times already this week of the cosmic cliffs in Carina. So part of why I'm excited about what JWST can do for us for star formation is looking at these kinds of high-mass star-forming regions where we want to understand how the high-mass stars are affecting the star and perhaps planet formation around it. So to start by getting a little bit oriented, we're in the Carina region here. This is about 2.3 kiloparsecs away, the next spiral arm over in our galaxies. So you can see in this optical image here on the left, the big H2 region of the NGC 3372, I think what most people think of when they think of Carina. But over sort of in suburbia, if I may, in the box here is NGC 3324, the target of the JWST observations. And it's worth a moment to think about where we are, because if we're interested in how high-mass stars are affecting the gas, we want to know which high-mass stars are doing the damage. So if we look at the MSX image here in the middle, you can see that the sort of hot dust, the red emission, doesn't connect between the center of Carina NGC 3372 and NGC 3324, just to make the point that it's different high-mass stars impacting the gas here. So there are about 5 mid to late O-type stars ionizing the region. And so we want to understand and sort of the impact of feedback here. So we maybe think of supernova as a primary form of star formation feedback. But more and more, we're thinking of pre-supernova feedback and trying to understand what that does, say, in terms of shaping the star-forming gas that the supernova eventually explode into. So the bubble shape in NGC 3324, or the super bubble of, say, the Carina main region. I think more attention also paid recently to how this feedback is affecting the ongoing star and planet formation within these regions. So for example, if I'm thinking of a star-forming region, I might have thought in the past, okay, a temperature of about 20 Kelvin, which in this temperature map here would be an orange color. Those red crosses are the high-mass stars, by the way. You'll notice there's not a whole lot of orange on this map because these regions are quite hot because they're heated by the high-mass stars. So the question is, what does this mean for the ongoing star and planet formation? And I think one of the big legacies of the Hubble Space Telescope was actually showing us exactly what this can do to star and planet forming regions with these famous images of the proplyds in Orion, where we can actually see the evaporation of planet forming disks in the center of the Orion region. And I think one of the reasons to be particularly excited about the James Webb Space Telescope is that it allows us to look at a much broader range of regions. We're no longer confined to, say, our nearest and favorite examples of low mass star formation or high mass star formation, or our favorite high mass star forming cluster that starts to get us to the kind of star forming conditions that allows us to talk to our extragalactic colleagues. So we can start probing a broader range of parameter space. And we can start with NGC 3324. So this image from Klaus's paper nicely shows us where in NGC 3324 we're looking. It's this bright ionized portion of the western part of the bubble. And the thing to note about this is it's not the most active star formation in NGC 3324. You can see in the Spitzer image that there's a lot going on the bottom of the bubble. And I make that point just so that we're thinking about this as sort of a quiet portion of the region. before we realize just how much is still going on in a kind of quiet portion of the region. So if we look at the public release image, you can see that there are a few interesting things going on here. We can blink back and forth with my favorite representation of this that makes the protostellar outflows really pop out. So we can sort of blink back and forth a few times because it's 9 o'clock and we're under-caffeinated. And if you go through this enough times, you can find more than 24 of these outflows. Those are going to show up as red in this particular color coding. So we can see, say, the biggest and most prominent thing here in the continuum subtracted H2 emission. And we're going to take advantage of the incredible image quality. You can get the real structure of this outflow, so not just the prominent bow shocks, but you can see that it's a bipolar flow. You can see that it's probably more than one outflow. So we can see at least 2 in the molecular hydrogen emission here. There might be something like 5 coming from this complex of stars. If we look on the other side of the region, we can look at this peculiar pair of protostellar outflows, and I think it's a really nice illustration of the value of not only the quality of the imaging, but the stability, what it would do for protostellar outflow science. So for example, there's a bright reflection nebula associated with one of these sources that very cleanly subtracts out when you remove the continuum emission, allowing you to look at the structure of the jet very close to the driving source. And again, with the stability, one thing that we would like to do is come back in a few years' time and repeat this image and see how the blobs from the jets have moved, both to get the velocity of outflows that are sort of smacking into a cloud as they're being ejected from the stars, but also to understand what goes with what. So with this particular outflow pair, we've got a bunch of knots that kind of sit right between the 2 outflow axes. And the question is, where are they coming from, and what does that tell us about how these sources are evolving and moving? We can get a first taste of what that looks like by comparing the Pasch and alpha images that were obtained with these early release observations and comparing them to H-alpha images that were obtained with HST in 2006. So we've got pretty comparable image quality, but a time baseline of 16 years. And you can use these to compare to measure how these blobs are moving. And again, the sharpness of the images is particularly important for things that are blobby and not necessarily point-like. So we can do this for things that are traced by ionized gas, so mostly outside of the cloud in the H2 region. And nevertheless, there are a lot of blobs that we can measure. So this gives us a sense of how fast things are moving in the H2 region. It also gives us a sense of what goes with what. So for example, we've got a collection of blobs here in the lower left that if you just look at a single image, you might think, oh, okay, these are a couple of things associated with the same flow. But when you can measure their velocities, you can see that that's at least 2 orthogonal flows. So lastly, when we have these similar resolution images tracing the ionized gas and the molecular gas, we can start to put pieces together and see things as they're both inside and outside of the cloud. So this is a particular interest of mine that we can see, say, the molecular outflow that shows up in red in this color image. And we can look at the motion of 2 shocks just outside of the cloud. Those are seen faintly in blue in this image, and see that their motion suggests that they come from exactly the same jet axis. So this tells us something about how this jet is moving. This also tells us something about how the observables, so to speak, change when you're inside and outside of the cloud. A particular interest of mine, again, in how high mass stars change what things look like. So using this incredible imaging quality, I would say, is one of a primary goal for outflow science, because what these things look like is a big part of how we answer the questions about outflows. What is the duration of the outflow driving timescale? What is the duty cycle of timescales? You basically have a historical record written on the sky when you have an image of an outflow. So for example, we can see there are 2 very prominent bow shocks, but with these incredible images, we can also see that there are several fainter features further down in this image. And this tells us that there were previous accretion bursts from this source, and it tells us that the axis that this outflow is moving along has changed since those accretion bursts. We would also hope this tells us something about how stars form. We can see these peculiar X-shaped things where we've got multiple outflows that are sort of perpendicular to each other. We have a couple of examples of outflows that are strangely parallel to each other. So we can look at the image and see that at the present time, the driving sources of these outflows are too far apart for us to think that they are that they were born from the same protostellar core if they never moved. So we could maybe come back in time and see if the driving sources of these outflows have moved. But we can get a hint at what might be happening if we look at the morphology of the outflows. If these 2 stars are driving an outflow as they move apart from each other, then we expect that they would trace the outflows would trace a C shape on the sky pointing towards each other. I think we could squint and debate, if I don't stand in front of the image that I'm talking about whether or not this is a C shape that we're seeing here and whether or not that might explain some of the blobs that we see between the 2. but it's a question we're interested in, trying to understand why the observed binary fraction of young stellar objects appears to decrease with time. Finally, we want to look at the orientation of the jets throughout the cloud, trying to see if there's a preferential alignment that might suggest that there's a large-scale magnetic field tracing through the star-forming cloud. We don't have any particular evidence for that in this sample, consistent with what we've seen in other low-mass star-forming regions. We can also just use outflows as a tracer of star formation. So if I just look at where we're finding outflows in this image, so that's going to be little boxes and labels in this particular image, you'll notice that a lot of these are sort of close to the edge of the cloud. So often when we're talking about star formation in high-mass star-forming regions, the idea of triggered star formation comes up. Does the feedback from the high-mass stars compress the gas and lead to the formation of new stars? So stars forming near the proximity of the edge of the cloud is certainly suggestive, although I will note that most of these outflows are also found towards the center of the image, where the colors of the image would suggest we have a higher degree of transparency. Nevertheless, the suggestion is, again, if high-mass stars are carving the gas, you might form dust pillars. And at the head of those dust pillars, and we have a couple of famous examples, again, from the Hubble Space Telescope in the Carina Nebula, that have been interpreted as evidence of triggered star formation. This has been suggested also for NGC 3372 based on the location of protostars found with Spitzer and Herschel, again at the heads of dust pillars. So one of the reasons to be surveying more regions and trying to come up with more statistical samples is to sort of address this question, is this actually triggered star formation or is this just erosion? And I will simply note in these ERO images that the most prominent pillar in this image does not have a jet associated with it. Unfortunately, this falls just outside of the area imaged with MIRI, so we don't know if there's a red and very young source lurking within the pillars. But in some sense, we don't really care if star formation was triggered if it doesn't really change the outcome of star formation. So we're interested in things that might be different in gas that is affected by feedback. Do these higher temperatures change how things fragment? Does this alter the IMF or the binarity fraction? Does this enable different chemical pathways in the gas, something that we might care about for planet formation as we have more and more evidence that the chemistry in planet-forming disks is inherited from the cloud? So to do that, what we really want to do is trace down examples of individual low-mass sources forming in these regions and study them in detail. But if I go and look at my favorite submillimeter survey, which if I'm going to do over a large scale is probably going to be with a 30 arcsecond beam, and I've just put a couple of examples of that on the image here, you can immediately see the problem, right? In each of these circles, we have about 3 to 5 different outflows. I'll probably get some emission. I'll probably have a hard time interpreting it. So I would also argue that a collection of jets in a high-mass star-forming region is an excellent, basically, finder chart for a high-resolution observatory like ALMA, which is something that myself and others have done using some of the jets in the Carina star-forming region. So just 2 examples here. One, if you were, say, looking to measure the size of circumstellar disks in these feedback-dominated regions, you'll find marginally resolved emission if you point with the largest baselines and the highest resolution possible with ALMA. But nevertheless, you can be reasonably confident that you understand what you're looking at because you have very good constraints on the orientation and inclination angle of this system because you know your jet. And similarly, I have used the kinematics and morphology of another outflow to try and understand the peculiar kinematics of a system and the gas within it that we think is actually a pretty good example of triggered star formation. So just to step back a moment and look at NGC 3324 as a whole again, and just remember, this is more than 24 molecular outflows. We've got several ionized jets in this region that's a relatively quiet portion of this high-mass star-forming region. And I think in that way, this is an excellent example of the power of the James Webb Space Telescope to be really changing our view of star formation, and in particular, star formation in regions that are affected by high-mass star feedback. So thank you very much for your attention. I'm happy to take any questions.
Thanks, Megan.
Thanks for the great talk. What is known about the protostars in particular? I mean, do you know much about their individual masses? What is the most massive protostar that's forming out of these 20?
So what do we know about the protostars at the moment? So that's a great question. Not much. So for 3 of these outflows, we have identified the driving sources from previous Spitzer catalogs. Those are going to probably be 2 to 8 solar masses because of the lower sensitivity of Spitzer. We can see in most cases something that looks point-like on the axis of the driving source, and I would be happy to follow up with you about masses once we're more confident about flux calibration to try and do something more detailed. Yeah, thanks.
Margaret Meixner from Sophia. Great talk, Megan, and amazing drive to just dive in there and get the results out. Do you imagine that you might find the lower mass pre-main sequence or young stellar objects by combing through the data, like the MIRI and just the photometry?
So that is certainly the hope, that we'd be finding lower mass stars through the photometry. We're also hoping that what we're finding are jets and outflows driven by lower mass stars. So I picked a couple of big and bright examples, but we see a lot of fewer and fainter things. One of my favorite examples is actually hiding in the corner of one of these images. Here, we have all kinds of things that we hope is actually giving us a sample across a broader range of stellar masses, and that would certainly be another question we want to look into, or how are the outflow properties changing as a function of the driving source mass.
Okay.
I have a couple of questions online. We have a question from Bill Green that says, is the CN radical a good tracer?
Is the CN radical a good tracer? That is a great question. If you have thoughts, I'd love to chat. But off the top of my head, I don't yet know.
There's also another question online from Samuel Federman, who says, do you have velocities for the HH objects by comparing to the Spitzer epoch? How soon might you be able to go back for a second epoch of JWST data and resolve the motion?
Okay. So we don't have any proper motions comparing to the Spitzer images because nothing particularly looks like an outflow in the Spitzer images. Again, this is a case where we really need the angular resolution of JWST. So, looking for motions of things in the cloud, we expect that they would be a little bit slower than the things that we're seeing in the H2 region because they're probably bashing into more stuff that will slow them down. Trying to do the math in my head. I think we need a few years, like 3 to 5, but please don't quote me on that until I can actually do some numbers.
Thanks. Can we thank Megan again for a great talk? Thank you.
Can you hear me? Yeah.
So now we're going to hear from Divakar Maya going further out to NGC 628. So.
Thank you. First of all, I thank the organizers for giving this opportunity to give this talk, and also to the JWST decision makers to making the data immediately available to the public. And the entire work that I'm going to present today is archival based. And the galaxy that I'm going to describe is NGC 628, and this is popularly known as the phantom galaxy. This phantom appearance comes because of so many holes, which are in fact interstellar bubbles, which are created by the feedback effects of massive stars through the stellar winds and supernova explosions. But there is one bubble sitting there, which is very, very big, and that's the bubble I'm going to talk about. Let me see. Yeah. So in fact, the bubble in that image is best traced in the filters, so which are in the mid-infrared, and especially in the 770 filter, which intercepts the pH molecules there. So at the distance around 10 megaparsec for the distance for this galaxy, the diameter of the bubble is around 1 kiloparsec. So it's a huge bubble, and we used how are we creating this kind of big bubbles? the most popular idea is through multiple supernova explosions, but there are other exotic processes that can also produce these kind of big bubbles. One of them is a gamma ray burst, or a high velocity cloud can impact on the disk and producing this kind of big bubbles. But it looks like for a long-living, high-contrast bubble, you need to have like a continuous supply of energy, which is best done by these multiple supernova explosions. How do we distinguish this? Well, if it is due to multiple supernova explosions, then there should be a remnant cluster of the low mass stars. So what we did was to look for a remnant cluster at the position of the bubble and to establish whether the method works. So if we find it, then it will help us to understand the conditions that are required for creating such large bubbles. So I use this opportunity to thank all the FANGS group to keep all the data available to the public, where they have a fantastic collection of multi-band data. We used all these data to map the bubble in the different phases of in ISM, and also to obtain the kinematic of the shell, and use the archival HST data to map the stellar cluster along with the JWST NIRCam images. So here are the results of the multi-phase morphology. You can see that on the left top you have the MIRI images tracing the pH molecules. Then you have H-alpha tracing the ionized gas, CO tracing the molecular gas, and H1 tracing the neutral atomic hydrogen gas. So same bubble is traced everywhere. The contours there correspond to the one at the 770 filter. And however, the majority of the mass of the bubble is in the molecular form. We measure around 20 million solar masses for the bubble for the shell mass. So we measure the velocity of the expanding bubble, and we get a value of around 12 kilometers per second for the expansion velocity. Okay, so I want to focus the attention on the stellar population that we are looking for inside the bubble. So here I combine the images for the HST and the NIRCam. So in the increasing order of wavelength, on the left, top left, you see the HST image, the blue band, whereas the last image is 3.6 micron image of the NIRCam instrument. So you can see that on the left there is clearly a overdensity of stars, which cannot be distinguished in the NIRCam images. So this is best seen in this color combined image, where the blue stars are from the HST, red ones on the NIRCam images, and it's very easy to see that all the blue stars are like confined within the bubble, and at the outer boundary of the bubble you have the H-alpha emission, indicating that there is also a recent star formation at the boundary of this bubble. So, well, we are looking for this stellar population, but we are expecting some cluster, but the stars are distributed over almost a kiloparsec size, which cannot be a simple cluster, so it may be a destroyed cluster, and we are also seeing this evidence for probably triggered star formation. So I will be exactly answering these questions in a minute. So in order to characterize the stars that we see inside the bubble, so we used some of the surrounding disk regions and obtained the star formation history of the bubble stars using the standard technique of color magnitude diagram. So we use the parsec isochrones along with the Bayesian technique to find or to associate isochrones to the stars. So here I have plotted the isochrones between 3 to 50 million years from top to bottom, and this is the CMD for the bubble stars, whereas this is for the background stars. So I'll move it back and forth just to, you can, oops. So you can clearly see that there is an excess of stars inside the bubble. So this is expressed best using the star formation history of each of these regions. In red, you see the star formation history of the background, and in the blue, you see the star formation history of the bubble stars. So beyond around 50 million years, star formation histories are similar in the two regions, but for stars younger than 50 million years, there's a clear excess of stars inside the bubble. So it's best seen when we subtract the disk star formation from the star formation inside the bubble. So we see this clear excess. So the star formation inside the bubble started around 50 million years ago, and since then stars are almost continuously forming in such a way that in the last 4 million years, which is 6.6 here, so there's no star formation inside the bubble. So the entire star formation, it was at a higher rate in the beginning, and later it looks like went on decreasing. And the amount of mass that is sitting inside the bubble in the stars that are formed in the last 50 million years is 10 to the 5 solar masses. So the question we asked is whether this mass is enough to create the bubble through to supplying this momentum and energy. And we use the standard hydrodynamical calculations of an expanding bubble in a uniform interstellar medium. And we find that the energy required is around 2.2 into 10 to the power 38 ergs per second, whereas a cluster of 10 to the power 5 solar mass, if all the stars are formed at a single time, it can produce 20 times more energy than what is required. So, however, I have showed you that all the stars are not formed at a single time here. So it was formed over a period of 50 million years. So it looks like the bubble is continuously getting energy, not all the energy at a time. Probably that is a trick to form these kind of big bubbles. Well, we have now ages for all the stars that are inside the bubble. So here I plot the spatial distribution of these ages, and I show here especially stars that are younger than 20 million years. Clearly, there is a tendency for these relatively younger stars to be closer to the shell rather than the bubble center. So, and also in the contours that I show the emission in the 21 micron filter of MIRI instrument, so which traces embedded stars. And but all these embedded stars have H-alpha emission, which is shown here in the green color. So green and the contours nicely coincide. So in the bubble boundary, you are seeing really very young star forming regions, which are probably a few million years old. And inside the bubble, close to the bubble, stars are younger. So I show this distribution in this plot where I plot the age of star against its radial distance from the bubble center. So the stars that are older than around 20 million years are found everywhere in the bubble, but younger stars are selectively located closer to the shell, suggesting that the star formation is proceeding from inside to outside, or it is like star formation expanding bubble. So in order to illustrate this, I make this cartoon picture where probably the first generation of stars formed in the center of this bubble, which created the expanding shell, and then the expanding shell created another generation of stars, which replenished with the more energy and momentum, like that, providing the energy to expand. So this process of collecting material and collapsing continued into the present day, and that's why we are seeing the triggered star formation now in the shell. You know? And so I'll answer the last question of what are the conditions that gave rise to this big bubble in the position that we are seeing. So probably there are two things. One, the entire cluster mass is not formed at a time, so that it was formed over a period of time, and so there was energy input continuously. And the second, the position where the first cluster was formed was not in the spiral arms. Instead, it is in the interarm region, where the interstellar medium does not have that great density gradient. So the first bubble that was formed could expand almost symmetrically, and that gave rise to further generation of stars. So that is the model we propose. So whereas those stars that are formed, clusters that are formed in the spiral arm itself, do not grow big enough before getting destroyed. So that's the reason why we believe that this particular bubble is very big. So just to end the talk, I'll give you the summary there and mention my collaborator in this work, which all of us are at INAOE in Puebla, in Mexico, and there are a few postdocs also involved in this work in this group. Thank you.
Any questions?
Question online
Let's go there first.
from Bill Green. It says, is there any evidence for a black hole in the bubble center?
As far as I know, I don't have any evidence right now.
Hi, Mikako Matsuura from Cardiff University. It's very nice results. So, but I would like to ask something about age and luminosity and isochron. The mid-infrared bands you have used to compare against isochron are quite polluted pHs. How accurate your age and luminosities in your estimate, if you consider the pollution of pHs?
Pollution of what?
Polyaromatic hydrocarbons in the flux?
Sure. I am using the CMD in the optical bands where pH are not affecting anything.
Okay, so the isochron you demonstrate are not used for the...
Yeah, the Hubble data. Yeah.
In that case, that's fine. Thank you.
Jonathan Tan, Chalmers, Virginia. It's very interesting results. When you say disrupted clusters, I guess you don't really see any hint of any kind of remnant core cluster, as far as I can tell. So you have a limit on what's left in a bound cluster in a relatively young region, which is surprising. So in this case, it seems like you're right, everything disrupts very quickly, but that seems unusual.
Yeah, usually the disruption time scale can be as short as like 4 to 5 million years when the first supernova events happen, and if there are a lot of gas in the cluster volume, when the gas gets expelled, the cluster can completely disappear.
So down to what mass, what kind of mass cluster are you sensitive?
In this study, it depends on the resolution, and it basically depends on the resolution. Whether I'm not able to detect here stars less massive than around 8 solar masses. So I'm not seeing really the very low mass stars which might be clustered. So that's a good question.
Well, from Guido, and then we better carry on.
Thank you so much. Wonderful talk. Guido De Marchi from the European Space Agency. Do you really need to have clusters? That's my question.
Well, it's believed that the stars form in clusters, so
they don't need
maybe
to.
not.
They don't need to.
Thank you. The problem solved.
You do not seem to be seeing, sorry, that's just a comment, but my question is, it seems to me you do not seem to be seeing any need for anything clustered. You showed very clearly that the stars are really diffuse, so we still do not know, right?
Exactly. Probably you don't need a cluster.
Thank you very much. Thank you.
Great. So, in the interest in time, can you follow up afterwards at coffee? Can we thank Divakara again? Thank you.
Thank you.
After that introduction to 628, I think hopefully we can segue effortlessly into the larger FANG survey. Stutter here.
Okay. Thank you. I'll jump over here. Good morning, everyone. I'm Jessica Sutter. I'm going to be giving a talk for the FANGS team, but I'm going to focus specifically on work I've been doing with Dr. Karen Sandstrom and Dr. Jeremy Chastanet, focusing on the PAH results for these first FANGS results. Okay, so before I get started, though, just a huge thanks to the entire FANGS team, collaborative community. I just recently joined and so excited to be in this amazing group led by Dr. Janice Lee. I can't put everyone's names on here or thank everyone because it's huge, but I do want to really shout out Tom Williams, Oleg Elgarov, and Christian Larson, who did just a heroic effort to make this data science ready so we could get you guys publications quickly from this JWST data. Oh yeah, and if you want to check out our survey paper is on arXiv, so it's Lee et al. And the arXiv information is here. So definitely check that paper out. I'll put it in the Slack after my talk. So what is FANGS? FANGS stands for Physics at High Angular Resolution in Nearby Galaxies. Don't ask me where the R went. That was a decision made before I joined. But the idea of this survey is to look at kind of star formation using observations across the EM spectrum. So we get information about pretty much every point in the baryon cycle, starting with kind of molecular cloud formation with ALMA, getting embedded star formation with JWST, and then star formation and stellar feedback with HST and MUSE. If you'd like to see more about the entire FANGS JWST survey, I encourage you to check out the poster by David Bilker, which has all of the information about the full survey. So the real reason we're all here to look at beautiful space images. So we're just going to go through the first 4 galaxies from FANGS. This is NGC 628. It's a beautiful grand design spiral. NGC 1365, a barred spiral galaxy with an AGN in the center. NGC 7496, another barred spiral galaxy with an AGN in the center. And IC 5332, this is our kind of low metallicity, another kind of face-on spiral galaxy. So in our first 4 galaxies, we have 2 AGNs, 1 grand design spiral, and 1 low metallicity galaxy. So a really nice subsample of our full sample of 19 galaxies that we're going to be trying to answer a whole slew of questions. Now, this is a 12-minute talk. I am not going to hit on all of these points. I want to point out, though, if you would like to learn more about how the FANGS JWST survey will reveal embedded star formation, Brad Whitmore has a poster that's focused more on this goal, looking at the embedded star forming regions in NGC 1365. I am going to focus on PAHs, though, which is what I'm really excited about, how we can learn about the smallest dust grains with this new data, and then, of course, focusing on those first 4 galaxies highlighted here. So just as a quick summary, what are PAHs? So polycyclic aromatic hydrocarbons, or PAHs, are some of the smallest dust grains in the interstellar medium. They can account for 15% of the interstellar carbon in the ISM, and they can be about up to 20% of the total infrared power from a galaxy. Why should we study them? Well, they're cool, and so I'm biased, but I think we definitely should. But they dominate the heating of the diffuse ISM and photodissociation regions, and they kind of regulate the ionization balance within the ISM. And this is because it's really easy to photoeject electrons from PAHs. So because of this, there's a lot of the free electrons in the more neutral ISM are coming from these PAH molecules, so they're very important for understanding kind of heating and photoelectric heating efficiency within the ISM. They are also an important absorber of interstellar starlight, so if you're trying to measure young stars, knowing what's going on with the PAHs is very important. And finally, they're detectable at what I would call high redshift. Maybe there's some debate about what that means now, but this is a redshift of 4 detection from ALMA of these PAHs, and with JWST, we can also get these higher redshift PAH detections. So understanding what's going on with these small grains is really important if we want to understand kind of the cycle of star formation within the ISM. The FANGS JWST is using multiple JWST photometric bands to try to study these PAH emission features. So we've got, this is the PAH model spectrum from the DRAIN models, and we can see that we have 3 NIRI bands NIRCam bands centered around the 3.3 micron feature. So the F335M band falls really nicely on top of it, and then two surrounding bands that can be used to subtract stellar continuum from this band. And then in MIRI, we have four bands. The 770 and the 1130 fall really nicely on the two most prominent PAW features, the 7.7 and 11.3 micron features, and then two additional bands, the 1000 and the 2100, which can give us more information about the large dust grains. So the first result, I'm just going to really quickly highlight that's super exciting, is with JWST, we can map the 3.3 micron feature in nearby galaxies for the first time. This is completely new. Spitzer IRS did not cover this feature, so we don't even have low-res data of this. The IRAC does have a 3.6 micron, had the IRAC 1 included this band, but there's too much stellar continuum, so you couldn't see this. So this is just very new, exciting stuff. Karen has a paper that's coming out soon, I promise, that shows how we can remove the stellar continuum. So this is just showing what the PAW emission from the 335 NIRCam band looks like in comparison to that stellar continuum. And we can see that the PAW emission is really nicely tracing the spiral arms near where we might expect star formation, and the stellar continuum is much more concentrated in the center. Oh, whoops, that was the wrong button. So I'm going to transition now to talk a little bit about other measurements we can make about the PAWs. So this is work I did with Jeremy Chastanet, which is submitted and hopefully will be on arXiv very, very soon. But we looked at the PAW fraction. So that the PAW fraction is this kind of, we're calling it the PAW fraction. It's our two PAW heavy bands divided by our large dust grain bands. So this is kind of PAW emission feature divided by large dust grain, so normalized by large dust grain emission. If you are familiar with the Drain and Lee dust models, it's proportional to the Q PAW value, but this is just a way of kind of measuring how much of our infrared emission is dominated by these PAWs. And what we can see in these two galaxies, the white contours are the H2 regions, and they seem to have the darkest colors, so the most purple colors, which are the lowest values of our PAW. So what this is showing is that in our H2 regions, we're potentially seeing the destruction of these PAW molecules. I'll also point out that there's PAWs everywhere. So that was something that maybe wasn't completely expected, but with the sensitivity of JWST, we can really see PAW emission everywhere in these galaxies, which is very exciting. We can also look at this RPAW value as a function of radius. A few things to note here. All four of our galaxies, very similar. So we see similar RPAW values despite the fact that we have four very different galaxies in our first four images. So that's the different colors here. The lowest one is IC5332, which is our low metallicity galaxy. So the difference between the gray and the other three colors might be just that low metallicity. We do see a slight decrease in terms of radius, but otherwise nothing huge here. Another kind of exciting thing we found is that if we have this, this is a little bit of a confusing x-axis. Sorry about the weird units, but this is our way of tracing kind of ionized gas to neutral gas. So H-alpha emission divided by surface density of gas. And what we can see is that our PAW fraction is pretty constant until we hit this value of 37.5, where it falls off. And that's the same value in all four galaxies. So what we're potentially seeing here is, again, kind of the threshold at which ionized gas kind of takes over and starts destroying our PAWs. So there's shielding from neutral gas no longer can protect them. In addition to studying the distribution of PAWs, we can also look at how the properties of the PAWs change across galaxy environments. So we do this using, again, the drain models for the PAW emission, which show that the 3.3 and 11.3 features are primarily produced by more neutral PAWs, where the 7.7 micron feature is produced by more highly ionized PAWs, and that the 3.3 and the 7 tend to come from smaller, hotter PAWs as well. So in our sample, this is NGC 628. This paper will have we'll have 3 of our first 4 galaxies. The black contours, again, are H2 regions. And I have 3 of our, the last one is 11.3 divided by 7.7. I'm sorry about that. It's covered up. But what we can see is that in the H2 regions, we tend to have hotter PAWs, and then also these darker colors within the H2 regions tell us they're more highly ionized. So using these ratios, we can get an idea of what's happening with the PAWs. Again, we can look at these as function of other inner gas properties, and we can see that so this is our 11.3 to 7.7, so higher on this y-axis is more neutral, lower is more ionized. The largest kind of obvious trend we see here is that as we go to regions that are more dominated by ionized gas, our PAWs are also more ionized. So maybe not crazy, surprising, but we do see a very nice trend here, which is exciting to be able to measure. Looking at instead the size of the PAWs, so this is kind of size/temperature. So as we go up, smaller, hotter PAWs, we can see the largest trend again is with our kind of ionized to neutral gas ratio, and we see this nice increase, which is telling us that we're seeing hotter PAWs in areas dominated by ionized gas. So those are some of our first results. I've tried to summarize some things here, as well as point out a lot of the other great work that's coming out from our collaboration. So JWST is just really an awesome tool for measuring the PAW emission in nearby galaxies at sensitivities and spatial resolutions that were previously unattainable. It's so amazing to see these structures, to see the PAW emission everywhere. We're just all very excited. A few things to highlight. We can now map the 3.3 emission feature. Definitely check out the paper by Karen Sandstrom that will be coming out soon if you want to see more about the how to do this. We see PAW emission everywhere. There's a lot of papers that will be showing this. There is one on the archive now by Jimena Rodriguez. There we see PAW emission changes, so this will be in the papers by Jeremy Chastanet and myself, but also in Oleg Elgarov's paper, which looks at this specifically within the H2 region, so definitely watch for that. We see PAW properties changes in stellar clusters as well, so the Dale et al. Paper, which is on archive as well, shows this. And then we see this potential destruction of PAWs within H2 regions. So a lot here, and just so much more to come. This is hot off the presses, NGC 1566. I think this was like last week or something. So we have just more and more data coming. We're so excited to share it all with you. So I'll flip back to my conclusions and take questions.
Thank you, Jessica, for this first insight into a fantastic data set and for covering so much ground. So I'm sure there's some questions here. Time for a couple. So.
Thank you, Jessica. Very nice talk. I'm Feng Wu from the University of Arizona. So I would like to know if I probably missed that, but one of the sources in your sample is the AGN. You didn't see anything different for that source in the PAWS radio distribution from other sources?
It's really hard to say. I'll point out, so the gray here is stuff that we've subtracted because of saturation. So with the PSF, there's a pretty significant amount of saturation from the AGN, so we can't say much about what's happening because of the AGN in our two sources. We do see some difference. So the blue line here is NGC 1365. There's a decrease towards the center. Is that because of the AGN? Maybe. It's hard to say with our sample at the moment, especially because we are not including so much of the AGN, the actual AGN measurements in this graph.
Okay, thank you.
Do you have any online?
Yeah, the questions online.
Do that, and then we'll skip to Jonathan.
Okay, so Christian Bausmer says, very exciting data and a great talk. Any plans for spectroscopic follow-up to get more information about the makeup of the PAW population, notably profile evolution?
We would love to do spectroscopic follow-up. I think there are cycle 2 proposals in the work. I think at this moment we don't have anything ready to go, but we are hoping to do that for sure, and looking at regions that might be best suited for it.
And there's another question online from Stacey McGough that says, how much does the 3.3 PAW feature contribute to the Spitzer broadband 3.6 light?
I don't have that number off the top of my head. The 3.6 IRAC band is large, so I think it's there. I don't know exactly what fraction it's going to be. So I think it's hard to say.
One more here, then we'll skip to Jonathan while we're switching talks.
Yeah, Brad Whitmore, Space Telescope Science Institute. Let's see, on this 1365 AGN question on pause, most of the pause in the center of 1365 are associated with the star formation. There's a lot of very superstar clusters, very young there, and that seems to dominate the pause there. Maybe one other thing, a couple other things I might mention is that there's also a couple papers, people like bubbles. There's two papers on bubbles out there, one on the void that you've already seen by Ash Barnes, and one where Liz Watkins has identified, I don't know, 2,000 bubbles in that galaxy. A quick item on Guido's earlier question is that we've got catalogs which are both cluster catalogs and association catalogs. And as you might expect in the void, there's both. So there's clearly about a half dozen clusters in that void. There's also lots of associations. So both of them are probably driving the void.
Thanks for the nice talk. Are any of your PAH metrics, do they calibrate or correlate well with the far ultraviolet intensity, which we could then use?
I am not. So I know there have been, so Adam Leroy's paper, which again has a referee report, I think, is the most recent news. It's very long, maybe unsurprisingly, but he is looking at the PA correlation with different star formation rate indicators. I don't think they do far ultraviolet or ultraviolet, but they see really nice correlation between PA emission and other star formation rate indicators, and some differences than what has been seen with the previous WISE kind of IRAC mid-infrared tracers, but that should be, I know they compared to CO, which is very different, but I think he also compared to H-alpha, I think. Sorry.
Great. So if we can thank Jessica again, we'll switch over. Okay, next up we've got Yaolun Yang, who will tell us about things closer to home with long-awaited studies of protostars.
All right, sound check. Am I sound okay? Good. All right. Well, first of all, I would like to thank everyone who make web happen. And as a user, this is an absolute privilege to be able to hands-on play with data and get used to this amazing facility. And so today it's my pleasure to show some of the first results from our Carina's program, which is try to understanding how the complex chemistry evolved at the onset of star formation. So before diving into that, I just want to acknowledge that this is teamwork. We have a fairly small, compact team, but we have a lot of diverse expertise and early career scientists that are all taking parts of different parts of analysis, as I will show you just in a bit. So one thing that in the last decade or so, we start to see, this is ALMA observation in radio, we started seeing tons of emission lines toward embedded protostars. Those are protostars still forming, still have a lot of material around it accreting, so still growing basically. And we see this like basically a line forest in there. And you can to zoom in, you will see a lot of the emission line here. They are all rotational transition for very complex molecules. Some of here are like ethyl cyanides, mesoformate. Those are the things you will learn on organic chemistry. So that's already pretty exciting. Like you see very complex molecule form at just when the star just formed. And there's even more exciting things, like there's some studies also found that the complex organic molecules, so-called COMs, in this embedded protostar is similar to what we found on comets. So this suggests there's some inheritance going on, perhaps from protostellar stage to planetary stage. Yeah, so then obvious question is like, how do we get this molecule? How do they form? So the current paradigm is that when we have this is the dense core, we have the core center here, you can see it's slightly denser. And once you have a star form, you start heating the dense core from inside out, create these chemical gradients. And then various different chemical reactions can occur at different parts of temperature and densities. And outside of like outer envelope, the temperature is pretty cold. A lot of the molecules and atoms were frozen onto the dust grain. So what happened is that, for example, we have the carbon and oxygen frozen here. The hydrogen can, through hydrogenation, basically attach on those atoms and form like slightly larger radicals. And as the temperature increases a little bit, this radical will gain ability to kind of react with each other, form a larger molecule. At this point, for example, we can form methanol, but they are still all locked on the grain. We cannot see it with ALMA. They just don't have any rotational transition we can see. It is only when these dust grain fall down to the inner part, when temperature is high enough, like above 100 Kelvin, that they get thermally desorbed and put into gas phase. That's where we can see those rotational transition. That's all the emission line we see before. And it's just highlighting that there's a lot of things going on in the ice phase on a dust grain that is normally not probed or only inferred from gas phase observation. And also recently, there's an observation and modeling effort, like also highlighting that there's a lot of more complex or like lesser known reaction can occur in low temperature region that really boost this complex organic molecule formation at pre-stellar stage. So, okay. So what about those things in gas phase? Are these just like one or few sources that we have this kind of effect? So we actually did a survey last year, like put out a survey last year, looking into 50 class 0 and class 1 protostar in Perseus in molecular clouds, and just try to look into basically answer the question that is this rare, like is this typical? And what we found is that there's about almost 60% of the sources we survey has shown emission of this complex organic molecules. About 40% does not. But it also basically suggests that this is not rare. This is something that perhaps most of the protostars will go through it once in a lifetime something. So this is something we need to really understand to incorporate to our understanding of star formation. And as I mentioned before, a lot of this is what we see. This is our gas phase columns that we see with ALMA. A lot of these, like columns are in ice. We don't really see it with ALMA, and that's where GEMFlip comes into picture to really understand what's going on in ice. So and to me, that this is sort of like a two-man question about trying to trace the origin of its gaseous complex molecules. And the first one is a comment we sort of try to understand it with ALMA right now. But then the second one is really that we really need Webb to redo it to understand where and how these molecules form. So I would argue that ice chemistry really holds the key for this question. And so what we do is that we can use the protostellar light as the background light, and we just point our telescope to it. This background radiation will go through all of the ice along our line of sight. And those molecules cannot rotate, give out emission, but they can vibrate and can take out, and those vibrations will take out energy in infrared wavelengths. So we see absorption features in infrared spectrum, and then we can associate that and try to quantify them to derive, identify ice species and quantify their abundance. And so this is like the main two questions I really want to, like our program try to tackle is that we see some sources, like more than half the sources have come, less than half of the does not. Is it real? Is there something they just intrinsically chemically evolve differently? Are those sources without complex molecules also don't have any complex molecule on ice? So, and also just use this ice plus gas measurement set together with ALMA and JWST to really benchmark our understanding of how column formation and evolution in star formation. So that's how we put together this Carina program. And what we do is that we acquire about 25 hours MRS observation for 4 protostars, try to get full spectrum from 5 to 28 microns. And we just put our IFU toward the source center. This is a really nice picture of a class 1 protostar, L27. And so we have this kind of IFU footprints, and then for each pixel, we're hoping to get a spectrum something like this and these are highlighting region are specific features that we really want to look into. And not yet. So, and so our survey design, we have 4 sources, and these 4 sources would choose those sources specifically to be able to test those 2 questions we raised earlier. So we kind of populate these 4 sources in 2 dimensions. One is luminosity to look into the thermal structure effect to the thermal distortion and evolution of complex molecules. And also they all have, there's 2 categories that have converge, comport. That's all categorized in in gas phase, so allow us to look into the diversity part of questions. So we hope by having these 4 sources that give us enough contrast in our sample to address those two questions. And in July 20th, we got our data, which is the day before I moved to Japan. I was downloading the data in Boston airport, really exciting. Yeah, so we got these data back then. They're gorgeous data. You can see these are absolute absorption feature that we can see. But the crazy thing, at least to us, is that there's so much detail that we can tell. Like if we zoom in, you can see there's some kind of wiggle here, there's some inflection there. Like there's just so much fidelity you can do and just demonstrate the power of JWST. We can even see potential signature of some organic species that haven't been firmly identified yet. We're still working on identifying them, but at least we see some tentative feature about that. So going to, and then in this kind of wiggle region here, we see these are not noise, these are all emission line. And yeah, and these are emission line, these are warm, CO, and water lines. So these are just something that we're not designed to look into, but it's just everywhere in our data. So this is ongoing analysis led by Collect and Klaus. They're looking to try to understand the physical condition of those where those molecules come from and where they are, etc. And yeah, so this again just demonstrating how much we have gained by going from Spitzer to JWST. The fidelity really just changed a lot. Like with Spitzer, you can see there's absorption feature there, but you have no idea what does it look like in terms of its detailed shapes, and those minor features is just so much better with JWST. Yeah, so again, like I mentioned, we see tentative hints of perhaps some organics feature here. Here, it's just me labeling where the laboratory data suggests the absorption feature of those molecules are, and on the left, this is where the lab measurements is for. So this is where we really need to talk to laboratory people to understand what they're measuring and how they apply to our data. So this is still very, very well work in progress, try to iron out each of those identifications. So for example, one thing we're working on is to just do a multi-component fitting for all of the ice features and kind of putting different mixture to see which one works, which one does not. So this is ongoing analysis led by Jaeyoung Kim and Chunghwa Kim in Korea. We also are working on a full forward modeling from physical model, inputting ice and dust. This is a work led by Jenny Bergner and Neil Evans and me. We're basically trying to do multi-approach and try to figure out how we can better model these kind of ice. And we also have mirrored parallel imaging turned on. So this is our sources again. This is in RF3 Spitzer image. And so we have our on source pointing, look like this. This is MRS. We turn on the parallel imaging. Good. And we have our dedicated background, which is here. And it just so happened that our parallel imaging kind of go through as part of our source. It was like, wait, what? And then we're looking at our data. It's like, here it is. We got one part of outflow in our mirror imaging. This is a total surprise. And again, we also have some smudges and everything. I was talking to Galaxy people yesterday to try and figure out what they are. But these are just really cool. Like, and we see this kind of shell-like structures here. They've never been seen before with RX2. Like in so many, and there's like scatter lines, and we can identify there's like 4 shells perhaps along the outflow. We can actually see there's a proper motion difference between from Spitzer to Webb. It's about 17 years timelines. They move about 2 arcseconds, and these kind of shell structure are very similar to what Yukio Okura has seen in her ALMA data to look into like molecular outflow. So she's currently leading this analysis and try to figure out how to make sense of all of this and what does it mean? Like how do we kind of have a holistic picture to explain both the infrared and also the submeter observation. So in the end, I hope I convinced you that we're now at a pivotal point that we can use JWST to really expand our understanding of ice analysis. These embedded protostars, they have lots of very interesting chemistry going on with powerful mirror and also near spec data. I think we'll see more results coming out in the coming days or even coming months. So thank you.
Apologies for the color bar here, but the it wasn't there for the folks online, so they got a clear view. So any questions in the room?
Hi, great talk. And maybe a bit of a technical question. You show this beautiful spectrum of the MRS, and it's quite a bright source, and it's perfectly stitched together as a continuous spectrum. And I was wondering, what did you do to achieve that, and how would, especially look at broad features, and you measure this depth, this might be very important to the interpretation.
Yeah, so, what we do is we did a spectral aperture extraction basically, and that aperture is go with a beam. So we do this is a 4-beam extraction. So your aperture grows as functions of wavelength. This is basically based on the fact that we see the source and pretty much look at the point source in our data set. And after that, there's some medium scaling, but the scaling is very, very minimum. And we have a figure in our appendix that actually show the difference that before and after scaling. Even if I don't do any scaling, it will be just fine. So yeah, so this is amazing. Yeah.
I have a question online. Bill Green says, nice talk. Any evidence of deuteration of the molecules?
We haven't really looked into that, so I don't know.
There's also another question online from Nolan Habel. Says, can you talk about what chemical traces are being observed in the jets you see?
Okay, yeah, so I have a slide for that. So yes, so we have, this is extraction at sort of like outflow position. And so we have about 8 molecular hydrogen lines, and also we have a bunch of ionic lines, iron 2, neon 2. We'll also have like nickel 2 maybe, and there's sulfur 1s. And so the interesting thing is that those ionic lines, and they trace like a jet-like structure. These are a continuous subtracting image. And while the H2 line seems to trace a sort of like a little bit more wider angle shock, maybe in the outflow cavities.
Okay, can we thank Yalon again? And we'll...
Thank you.
Next speaker.
How do I?
Sorry. Share your screen.
Hey.
Hey, that sounds good.
Can you see the slide?
Yep, we're set up in the room, so all yours.
Okay, thank you very much. First of all, thank you for giving me the opportunity to present the results our group are obtaining with the JWST data that are public. And we are specialized in the analysis of stars in dense stellar fields like globular clusters, close by galaxies. And here you can see some images we obtained with the images collected during the IRS program 1334. And to obtain, we studied these stars, and to obtain the best photometry and astrometry of these stars, we need we need to use PSF fitting. And for this reason, we need to use PSF models that are well modeled. And we know that, especially at short wavelengths, the JWST PSFs are undersampled. So by using tools that we have already used for HST and other instruments, we modeled this PSF. Moreover, we also extract the geometric distortion of a NIRCam in NIRS camera, and all these works are based on the use of the data collected during the IRS 1334, but also the calibration data, the calibration programs 1476 and 1510. And all these tools will be used for the next, for the data that will collect it in the next proposal, like the one of principal investigator Bedin, go 1979. So First of all, in our first work, we modeled the JWST NIRCam PSFs by using the data of M92, and this is an example. You can see the different shapes of the PSF in different filters, both in short wavelengths and long wavelength channels. The PSFs of NIRCam are on average undersampled, especially in F019W, and this undersampling brings to a degeneracy between the flux and the position of the stars. And so to model these PSFs, we use the empirical approach developed by Anderson and King for the wide-field camera, wide-field planetary camera 2. So we used all the detailed images of the global class M92 to model the PSF to break this degeneracy. Moreover, we used a spatially varying PSF to take into account of the different shape of the PSF in different location of the detectors, and for each image, after obtaining the library effective PSF, we perturb the PSF to take into account the time variation of the PSFs. And here you can see the original image, an original NIRCam image, and the same image after the subtraction of the stars that we fitted by using the tools we use. And we are still improving the NIRCam APSF models. And so we are still working on this, on not only NIRCam but also NIRIS. These are the first results of a work that we are preparing, and here you can see an example of the NIRCam APSF. Not only PSF, obviously after the extraction of the position and fluxes of the stars, we need to correct for geometric distortion to match images, to match catalogs that are collected in images that are detailed, or to match the JWST data with the HST data. In the case of NIRCam, we prepared a work that is now on archive, and we submitted this paper 1 month ago. We didn't receive any response by the referee. Anyway, we obtained that these maps that show that the NIRCam distortion is up to 10 pixels, while for the NIRIS we only have 1.5 pixels of distortion. After the correction, the position, the residual the position are only 0.2 milliarc seconds. So it is a very good solution, and give us the opportunity to match the JWST data with the HST data, as I will show you later. In our first work, we obtained the color magnetogram of the global class M92s. When we did this work, the calibration of JWST was not so good, so we used theoretical models and the HST observation of M92 to register the 0 point of each single detector. And so here you can see the difference in 0 point between the different detectors, and the color magnitude diagrams obtained with all the stars for which we extracted the photometry. And we obtained that the best color magnitude diagram is the F09 versus F09 minus F150 color magnitude diagrms that reach the bottom of the main sequence with a signal to noise of about 10, and we can observe stars with masses below the 0.1 solar masses. Not only stars in the main sequence, but also white dwarfs. We detected 24 candidate white dwarfs in the JWST data to have to confirm this the nature of white dwarfs we matched the JWST catalogs with the catalogs obtained, the UV catalogs obtained with the HST data collected during the GO 15173, and we found that 7 candidate white dwarfs were in common between the two data sets, and they lie on the sequence of the white dwarfs also in the UV data. Moreover, they will fit the tracks with hydrogen or helium atmosphere of white dwarf of the white dwarf cooling tracks. And here you can see also the 3 color images of these candidates white dwarfs from the brightest to the faintest white dwarf you can see in the color magnitude diagram. And expected results we obtained is the observation of multiple population in the main sequence of M92. M92 is a very metal poor globular clusters, and for this kind of globular clusters, it's very difficult to detect the multiple population, also with the ultraviolet filters. M92 hosts at least 3 stellar populations, as we can see in the pseudo color diagram of RGB stars obtained with the HST data by Milone and collaborators in 2017. Anyway, matching the JWST data with the UV data, UV HST data, we observed the spread of the main sequence just below the main sequence turn-off, and we observed that this spread, in particular, the distribution in color of the main sequence have a double peak. So we are not able to detect the 3 different populations, to distinguish the 3 different populations, but we divided this main sequence in 2 different sequences, and we follow with the average trends of these 2 main sequences in different color combinations. And we discovered that the 2 sequences form always 2 different groups of stars. So it means that it is real, it is not due to systematic effects of the photometry or JWST, and they probably they are the multiple population having different chemical properties. Not only photometry, but also astrometry. Here you can see the results obtained by Grigio and collaborators. And for M92, we used the proper motion to decontaminate the color magnitude diagrams from field stars, but also to measure the internal dispersion of M92 to have a check of the goodness of our geometric distortion solution. So we matched the catalog of JWST with the HST data collected in 2006, and we found the internal proper motion. We measured the internal dispersion of the proper motion, and we found that the results are in agreement with the other works, like, for example, the last one of the last is like Galata and collaborators. And also for the LMC, we did the same. We extracted the vector point diagrams of the stars in the LMC using data collected 16 years ago, and we found that the distribution of the stars remembers it is very similar to the distribution of stars found by Anderson collaborators in the vector point diagrams by Anderson collaborators obtained by using only HST data. So our geometric solution works very well. And these are just a quick look to our works in progress. This is one of the first color magnitude diagrams obtained by using NIRIS data of M92, and we are working on the luminosity and mass functions of M92 at different radial distances with the combination of NIRCam and NIRIS. And also, Bedin and collaboration is preparing a work on the star formation history of the WLM and Draco second galaxies. So that's all. Thank you very much for your attention, and questions are welcome.
Thanks, Nadia. Any questions in the room or online? Online.
Thanks for all the work you're doing on this astrometry and stuff, because we're finding similar problems in our data, and it's just reassuring that someone's blazed the way on how to fix them. So thank you.
You're welcome.
Yeah, thanks for a great talk. This is Tim Carlton from Arizona State. I was wondering how your PSFs compare with the model web PSFs that are produced.
We did not the comparison between the PSF models we obtained and the web PSF models. But I gave a look to them and the shape is the same, but because the normalization is different, so it is not so very simple to do a direct comparison between the two kind of PSFs. But anyway, yes, the shape at different wavelengths, at different in different filters is very, very similar because that are the stars. So yes, it is very interesting because give us the opportunity to have an independent check of the goodness of our PSFs.
Great, thanks. Can we thank Nardiello again, and we'll move on? So, final talk here for the session.
Yeah.
Just find your slides.
No, it's green.
Oh, okay. Okay, so to wrap up this morning's session,
Sorry about that.
Baltimore return. A warm welcome to
Yeah.
Matteo Carenti, who's going to tell us all about 47 Tuck.
First of all, I would like to thank the organizer for having me here and very nice conference. So I will talk a little bit about Global Cluster 47 TAC and the stellar population about it. So just a brief summary of our project. This is a small proposal, GEO2559. It's an international collaboration. The PI is Ilaria Caiazzo from Caltech. Our target is 47 TAC, very well-known globular clusters. As I said, it's a small program, so 20 hours of near-come observation, and here you have the setup. It's basically a 2x2 mosaic. The data were obtained in September, but we had, for one of the visit, so one of the tile of the mosaic, a guide star failure, so the data will be retaken in May. The main goals of this project are two, basically. One is the study and characterization of the brown dwarf population in this cluster, and the other one is the search for white dwarf with IR excess. In this particular talk, in these 10 minutes, I will talk about the second one, but I'm happy to chat about the first topic during the coffee break. And there is a very nice poster about one of our collaboration, Roman Gerasimov, about the models for the brown dwarf. So if you're interested, you can look at the poster and talk with me. So a little bit about the motivation and why we are looking for IR excess in white dwarf is the question when the universe was first capable of supporting life. I don't know the answer, but likely was preceded by the formation of the first planet. So when did this occur? There have been a study in the past on this particular global cluster, 47 TAC, and earlier work using HST. Was not very sensitive, so only for hot Jupiters, and they didn't find any evidence for planets. In another cluster, M4 has a planet, but it orbits around a neutron star, so the origin of this planet is unsure. So what we are doing here in this particular program is to look for debris, solar system debris in a globular cluster by examining the white dwarf for a near IR excess. Sorry. And why 47 TAC? Because it's a very well-studied cluster. We have a very nice...
Since there's no card that I had made this note card thing for one of those math classes that I was in, and apparently, Mary Beth.
CMD. Of course, there is the SMC behind the cluster, but since we have data spanned a range of time, we can proper motion clean, and as you can see, you have a Clearman sequence and the white dwarf cooling sequence. Here is an example of another cluster, and as you can see, it's much less populous, so it's not as good as the 47 TAC for this kind of study. So the second question is, why do we need JWST? Sorry, not HST, JWST. So we know that in the field, more or less 3% of white dwarfs with this temperature between 9,000 and 25,000 exhibit excess due to dust. And here you have two examples. And as you can clearly see, you need to go to the infrared longward of the K-band to observe this kind of excess in the IR. And HST, of course, has no capability to do it. And on the right, we have sort of the poster child for this kind of white dwarf with the Saturn-like disk. G2938 is the point, and rescaled, of course, to the distance of 47 TAC. And here there are a couple of models that for different temperatures. And it means that basically also from ground is impossible to observe this kind of white dwarf because they are too faint. So JWST is perfect for this kind of study. And why is important, of course, to have HST data? Because we know where the white dwarfs are and we know their magnitudes. So we have for all of them at least multi-band photometry. And I just want to point out that this is, of course, not 356. This, I blame it to working too much on it in the past, is 336 from HST. And so we have all this magnitude in the HST and blue filter, and we have model, and so we can basically know which is the set of this particular white dwarf that we are studying. So how many white dwarfs do we expect with infrared excess? So we know that more or less we have, as I said, 3% in the field show this IR excess. So knowing that for HST we have around 400 in our JWST field, 3% is around 12. So the probability of seeing 0 is very, very low. But also if we don't observe any white dwarf with excess, it's still a good result because it means that there is some difference between the cluster that in this case is different, the population and the metallicity from that of the field. And here, finally, I'm going to show you where are our pointing. So we are not pointing, of course, the center of the cluster because it's too crowded, too many red giants. So we are pointing the same field of HST here in the middle, so the blue one. And the cluster over there is on the right. So if you're looking, basically going over there for outskirts. And the black one is basically the blue shape. So this is the mosaic. And as you can see, we are missing the tile over there. So I just want to point out some of the challenges during the analysis. This is the stacked image that you derive from the pipeline. And as you can see, there is a lot of strange things in between. When I look at this first image for the first time, I said, oh, what's going on? And so if you basically compare the HST field that is aligned to Gaia and the different visits, you can see that if you pick a star, there is a huge discrepancy in position. If you basically trust the position given by the pipeline, that it means that there is some problem from the FGS alignment. So in this particular case, there is one field instead that is the alignment is not that bad, it's only 0.7, so it's easier to do the job of realigning everything. For the other one, it takes a little bit more of work to do all the realignment and rerunning in the pipeline. And as you can see, when you do the right alignment, there is a really good alignment between HST and JWST. And I don't know if it worked. This was a movie. I just want to show you. Yep. Yeah, I mean, it's something that we already expected. There are things that don't show up at all in the HST data, the blue data and JWST data galaxy that are completely absent in the HST and they pop up in the red. So it's nothing unexpected, but I still think it's really cool to show this kind of amazing size that you can do also in a stellar field with other things that are not there and they show up complete in the James Webb images. So finally, some color magnitude diagrams. So, and let me preface, this is just one of the tiles that I showed before, the one that I was able to align perfectly. So this is basically just one of the 6 fields that we have right now. And on the left, we have the CMD, HST, JWST CMD. With the short wavelength and long wavelength, and you can see there is the contamination by the SMC. But of course, as I said before, since we have this data from the past, we can proper motion clean, and so we can basically observe the clear white dwarf cooling sequence in both short wavelength and long wavelength. And I'm just gonna show you here this better, so it's highlighted, and I'm just zoom in on the 3 white dwarfs picked randomly from this sample. So, and I just want to say here is missing something, the points. I just posted on Slack the plot with the points. It was a really preliminary result. I was not able to do it before Thursday night, the deadline. So it's on Slack if you want to look at it. But basically, these are 2 models by the Montreal group that show what kind of excess you expect depending on the temperature. So for a 9K stars, there is 1 magnitude with the disk, and 25K at least 2 magnitude. And from the preliminary result that you can look in the Slack channel, the plot, we have at least 1 star that looks very promising. So as I said, these are very preliminary measures. We are still working, as you may know, about PSF photometry. It's still a preliminary things, but I think it's really exciting that we are able to observe this kind of white dwarf, and we are also reaching down to 9K, and we are going deep, and we are basically sure to compile all the white dwarf in this particular field, and also we are down in the Brandorf regime, so our science can be done clearly with this kind of observations. And yeah, that's it.
Any questions?
Thank you for this exquisite high precision work. How many did you find?
Sorry?
How many did you find? You say it looks promising.
Yeah, no, right now we are concentrating about the one above 9,000K because they were expected to be disk. So we have around 15, 16, and there is 1. But as I said, this is just 1 field. So depending on, you believe in the statistic, maybe there are around 6, 8 if it's true. And we are also trying to confirm, because we have, as you see from the plot here, there are more than, this is around 130 white dwarf. So, but as you can see from the image, it's really hard. Sometimes you have to look carefully at what kind of stars you are observing. I just give you a glimpse of what I'm saying here. I was, for example, I was sure about this one. I said, I found a very nice candidate. But then if you look at the 150, it's sort of isolated the star. So, but then you look at the 322, there is a galaxy over there. So maybe the excess is due to the galaxy, it's not the real excess from the star. So before trusting the result, you have to go back and look at the images, like sort of like the old astronomy. You have to look at carefully. But yeah, that's the number more or less, is 1 out of 20 for 1 field.
Thanks again for the nice talk. As part of your analysis, do you also have to do a geometric distortion correction? And I'm just curious how, also in comparison to the last talk.
Oh yeah. So
stable that is.
I think it's pretty stable. Yeah. Basically, I just sort of use what we have in the pipeline right now, because I'm biased. I was working with NIRCam, so, and I think there's room for improvement. For sure, the results show that they are definitely improving what we have right now. But I think for this kind of, in particular for the white dwarf, since we know the position from HST,
We have a question online from Loic Albert that says, are you sensitive to substellar objects, i.e. brown dwarfs, and study their cooling track?
Yes, that's the poster Roman presented. There are new tracks for the brown dwarfs, so you can look at the poster, but definitely, yeah.
Before we thank Matteo and all this morning's speakers again, can I just say thank you to each of you for keeping nicely to time and some good questions going after each. Just a quick announcement, later at this afternoon's coffee break, we're going to try and do a photo of those here and try and get people behind you on the screen for those online as well. So don't rush off to coffee later on. In the near term, can you come back here on the hour at 11 Eastern? So for those online, if you're back online in sort of 25 minutes or so, we'll resume here. And can we just thank all this morning's speakers again? Thank you.
on the JWST. I don't know for
You're Chris.
Yes,
Awesome.
hi, I'm Chris.
Hi, I'm Susan. Good to meet you. Okay, so yeah, just as high up as
It's fine. middle here. Yeah.
Are they sauntering?
It's always the way
the
after the break.
They're just cutting into their lunch. I thought maybe that was slightly more. We'll give it a go.
I didn't realize when I made it how horribly long my title is.
It's okay. It's at least descriptive. I know what you're going to talk about.
Yeah,
then.
right.
The timer. Okay, everybody, let's get in and take our seats so we can get on with our next section. So we learned a lot about the formation and life of stars, and now we're going to be going on towards the latter end of their lives in this session. So let me introduce Chris Aschel as our first speaker.
Hey, thank you. I'm Chris Aschel. I'm the new assistant professor at Virginia Tech. Today I'm going to talk to you about a couple of the programs we have to look at late-time spectral observations of different supernovae. So I'm a spectroscopist. There won't be quite as many pretty pictures as we've seen previously, but hopefully I'll show you why we need this spectra to understand the physics. And I want to say thank you to all the organizers. Thank you to everyone who's worked on James Webb over the past decades. It's been really awesome that you've got it to this far. And thank you to many of my collaborators around the world. A few of those are in the room today. Peter Hoflick, Eddie Barron, and my postdoc, James Storchese. And there's also many people which have helped with all of this. So despite being the best extragalactic distance indicators, we really don't know what Taiwanese supernovae are. Right? Do they come from the single degenerate system, which is a carbon-oxygen white dwarf with a non-degenerate companion star? Do they come from the double degenerate system, 2 carbon-oxygen white dwarfs? Are they a triple system where there's at least 2 carbon-oxygen white dwarfs with a third star? Is it a carbon-oxygen white dwarf merging with the core of an evolved star? So there's many different progenitor scenarios, and there's also many different explosion mechanisms. Does the explosion start with compressional heating in the center when you gain enough mass until you approach this Chandrasekhar mass? Is it some sort of outer helium detonation which drives another detonation into the center? Or is it some sort of outer carbon ignition where 2 white dwarfs collide or violently merge? And within these scenarios, these progenitor scenarios and explosion mechanisms, they don't directly link one-to-one. I'm not going to explain this in detail, but there's this huge array of how we can make these supernovae explode. But what we do know is that the primary thing that explodes is the carbon-oxygen white dwarf. And what we see is linked to the density and the temperature of the burning in the ejector. So here on the left-hand side, I have 2 models of different mass white dwarfs. The bottom one is a 1 solar mass white dwarf, where we have densities which go up to about 5 times 10 to the 7 grams per cubic centimeter. And here, when this burns, it makes some nickel-56, which is radioactive and powers the luminous display. Then it makes silicon, it makes sulfur, it makes oxygen. As we go up to higher masses, close to the Chandrasekhar mass, we get to densities above 1 times 10 to the 9 grams per cubic centimeter. At these densities, we make these stable ion group elements, these electron capture elements, such as nickel-58. And these densities are only found in white dwarfs with masses above 1.2. So white dwarfs, carbon-oxygen white dwarfs, which have to be made via accretion. So to look in these dense inner layers, we need to be looking at late time. So when the ejector is optically thin and we see emission lines which take us right into the center. We also need to be looking at wavelength regimes where these lines exist. So the mid-infrared is ideal for this. We can see nickel lines, right, at these epochs where it's very late. We know that nickel 56 is decayed, so any nickel we see will be from stable nickel. And we can see these nickel lines, and we see the center of the explosion where the high-density burning is meant to be. So to get these observations, we need to look at supernovae, which are very close. And this brings me to 2021 AEFX. So I did find out today that this is actually in the FANG survey. I didn't know this on Thursday, but we saw a beautiful image earlier from James Webb of NGC 1566. The 2021 AEFX exploded in NGC 1566. It's a normal Type 1a supernova. It was discovered by the DLT-40 survey. We followed it up in many different programs, including POISE, the Precision Observations of Infant Supernovae, which is the follow-up to the Carnegie Supernova Project. And here's a light curve in the optical, just demonstrating that this is a normal Type 1a supernova. This plot made by my student, Cassie Stevens. And we got LRS MIRI spectrum at 323 days past maximum light. And here's our spectrum. So 5 to 14 micron, amazing signal to noise. My postdoc, James DeCasey, is working on this. There's also a spectrum earlier with a paper led by Lindsay Clark, who's in the audience. She has a great poster on this, and we're working together to get this great time series. And the spectra shows us what we expect of a Type 1a supernovae nebula spectrum. Broad emission lines, which link to different parts of the ejector. And straight away, we see some interesting things. We see cobalt emission, cobalt 3. So cobalt at this phase is directly linked to the nickel 56. The nickel 56 is decayed to cobalt 56 to power the luminous display. We see a number of nickel lines, which at this phase are from stable nickel. Then we also see argon lines with this flat top profile. I'm going to take you through a few of these different lines and explain why they're so interesting in understanding the physics and explosions of Type 1a supernovae. And these lines previously basically weren't available to be studied or do use before the James Webb Space Telescope came online. So let me start with the argon line. So argon's a really important element in a Type 1a supernova explosion because it traces this material between the nickel 56 region and the silicon region. So any burning or mixing between those regions, we're going to see in the argon line. And we also see here that it has this interesting flat-topped profile. And the flat-top profile means that we have a hole of argon in the center of the explosion. So we see that we have argon, further out than 8,000 kilometers a second, but in the inner 8,000 kilometers a second, we don't have any argon. This already tells us that there's not much mixing there in the inner part between the argon and the nickel 56. Another very important line when we're looking at these spectra is this cobalt line. Now, this is a cobalt line. It's a resonance line. So the cobalt is produced from the nickel 56 decay. The resonance lines meet all the transitions go through it, and it's also an isolated line. When we look at supernova spectrum in the emission phase, we often see there's loads of overlapping lines. We've got mini blends. But because this is an isolated line, we can use it to really understand the distribution of the nickel 56. And we see two interesting things here. We see that it's not at the kinematic center of the explosion, so that it's offset by about 700 kilometers a second, which means the nickel is not in the very center, the radioactive nickel. And we also see hints that it might be shifted in peak towards the red side, right? So it's slightly red shifted away from us. And then the third interesting region is that we see blends of different nickel lines. So at these phases, these nickel lines are not from nickel 56, they're from nickel 58. So they're high density burning lines. The fact that we see many of these demonstrates that our density has to be in this explosion above 1 × 10⁹ grams per cubic centimeter. This means we had to have a white dwarf with at least 1.2 solar masses. Right? Previously, it was very difficult to constrain this before this data was available. So we can then take this one step further. We have the idea, we have an argon shell, we have a nickel 56, which is offset, and we know we have high density burning in the center. We can compare this to explosion models. So here we compare it to a delayed detonation model. So what's this? This is a carbon oxygen white dwarf, which accretes material until it's close to the Chandrasekhar mass. Then compressional heating starts in the center of the explosion. This compressional heating starts the thermonuclear runaway, which starts as a subsonic deflagration wave. At some point, it transitions into a detonation, and then you have a detonation, so a supersonic wave going through. And you can see, so this is a explosion which has a central density of 1.1 times 10 to the 9, so high enough to make these stable elements. It makes about half a solar mass of nickel-56. And you can see from the elemental distribution here that we start with the lighter elements at the higher velocities, the carbon, the oxygen, the silicon further in. And then the argon here, which traces this region between silicon and nickel, drops off at 8,000 kilometers a second, exactly what we see in the flat top profile, followed by a nickel-56 distribution further in, which is not in the center, and electron capture elements such as nickel-58 in the very center. And before we compare it further, we do the sanity check that does this actually produce a light curve of our object? And you see here that we get a really nice fit between our model and our object. So something interesting about this type of explosion is that when you have this point between your deflagration to detonation transition, this is inherently off-center. And you get slightly more efficient burning at the point between the deflagration to detonation transition. So what you see here is a plot cross-section of basically the mass fraction of nickel-56 in the ejector at a set time, where red is where most of the nickel-56 is. Now, this is the point here on the northern side where this deflagration to detonation transition occurs. And at this point, you get slightly more effective burning. Now, if we're going to observe the ejector, so this happens, we could observe it at any angle, right? So we can compute the cobalt-3 line at any of these angles, because it's an isolated line. It comes from the decay of the nickel-56, and it's a resonance line. So we can compute it from these different angles, and we can get these different line profiles. And these different line profiles of the cobalt-3 line can tell us how we might be looking at the ejector. Then we can compare this to our observations. So we see a preference for a minus 30 degrees viewing angle. Now, this is also seen in the data of the earlier spectra. Now, you might think I'm overindulging myself slightly because of this low resolution spectrum. So that's where we're going to go next. We're going next to get the medium resolution spectrum. But this is just one of the pieces of information along with the carbon and the high stable nickel, which paints the picture of this as a near Chandrasekhar mass explosion. So, we have this high central density in the center, shown by the nickel lines. We have the off-center DDT transition, meaning our nickel-56 is not in the center of the explosion, which is also confirmed here. And then we see the argon further out with that flat top shape profile. So straight away, just from one spectrum, there's many different areas of physics we can look at, right? We see with the stable burning, it's above 1 times 10 to the 9 grams per cubic centimeter. We see the flat top profile, the argon's far out, and we see the off-center nickel-56. So I also want to mention that we have this other program we're looking at, dust, mass loss, and explosions of massive stars. Here we're looking for molecular formation in core collapse supernovae. So what temperatures and conditions and densities does carbon monoxide and silicon monoxide form in type 2 supernovae? And we're getting spectra all the way from 2 to 22 micron with MNIRSEC and MRS. And we're going to be comparing two different suites of models to understand the conditions, early conditions for dust formation in type 2 supernovae. So I just want to say that, here we have this amazing spectrum. We can extract so much physics just from one spectrum. This one is indicating that it seems to be consistent with this near Chandrasekhar mass explosion. But as we go forward and get more LRS spectrum, and especially the MRS spectrum we're getting in the future, we're going to really be able to understand and look at this sample size to see which explosion scenarios and which progenitor scenarios exist in type 1a supernovae. Thank you.
Okay, do we have any questions? Online?
Margaret. So you talk about the MRS giving you accurate details of the distribution. Is it also going to be basically using the velocity structure to tell you that structure, or so you actually resolve it? I'm just curious.
So we'll be able to see the elemental distribution, because we'll be able to see the resolved lines, because especially in the central region, when we're talking about like the nickel-56 and the high density burning, these should only be, a couple of 100 kilometers a second for some of these elements. So when we have this medium resolution spectrum, we should be able to, for the elements right in the very center, really resolve where they are in the ejector. And this should be able to actually tell us put a better constraint on the actual mass and density of the burn-in.
And do you expect more lines as you get further out? Are you going?
Yeah, we expect more lines of electron capture elements such as manganese and chromium, which might actually indicate burning as high as like 3 × 10⁹ grams per cubic centimeter. And because the central density is linked to the white dwarf mass, we can then put tighter constraints on the white dwarf mass.
Very nice talk. So would two merging white dwarfs of 0.6 or 0.7 solar masses coalesce to the point that you could produce this kind of an event, or are we really talking about a single CO white dwarf of 1.2 plus solar masses?
Great question. So you could reach the densities required for that in the two white dwarfs, but because you could have two more central peaks of densities, you might not end up with these symmetric or slightly obscured line profiles. You might have double line profiles. Also in Taiwanese supernovae, we see no continuum polarization essentially. So we know these are very spherical explosions. So here we're really thinking of more of one white dwarf, carbon oxygen white dwarf.
One more question over here.
Very interesting results. I have a question about how to say modeling in the line profile. So I understood you put the spatial elemental distribution. Did you take into account the excitation of the line, such as electron temperature or electron density in the model?
These are full non-LTE radiation hydrodynamical models. Yeah,
that's great.
That's great. Thank you.
Online? Okay, let's do one quick one online, and we can maybe, Jacob, you can get up.
Yeah, so the question line from Bob Williams says, do you expect the nickel lines to show the same 700 kilometer per second velocity offset as the cobalt emission lines?
Great question. So actually, they should be, if we go back to the structure, the elemental structure, the nickel 58 should be, because it's in the higher density region, should be below the nickel 56. We expect them to have lower velocity lines.
Okay, let's thank our speaker again.
Thanks.
Oh, thanks.
Oh, yeah. You can hear me?
All right. Yeah.
Oh, sorry.
Our next speaker is Jacob Jensen.
Thank you. Hi, everyone. I'm Jacob Jensen. I'm a relatively new postdoc here, joining the group, the Transient Science at Space Telescope group. And I'm going to be talking to you today about a project based on this GTO program with PI Mike Ressler, who's a product scientist for MIRI. And I'm going to be talking about these unusual infrared transients that we've now been able to get some JWST spectroscopy for. And it's a bit of a spoiler if you happen to know this beautiful HST image of V838 MON and what kind of transient event that was, where you're seeing this very red source in the center, in the aftermath of the outburst, and then it had these beautiful light echoes. So we're going to be focusing on what's really going on in the center of this really red source and other sources like this. Not this one in particular, but, and this was all done in collaboration with our team, all these really fantastic people down here. Okay, so the type of transients we're going to be talking about mostly are related to these objects that are called red novae, or luminous red novae, the more luminous ones, which we believe probe the very final stages of common envelope evolution. And so this V838 MON object that you saw in the previous slide is now sort of a prototype, although it's a bit of an oddball, of this V838 MON class, now known as red novae, which show these very unusual spectral evolution features. So initially when it was discovered, it was an outburst of a variable star and was thought to just be a nova, but then it had this strange evolution where it got very, very red. So you can see that in the spectral evolution in this diagram here. And started to develop a very cool photosphere similar to a cool giant, dominated by molecular absorption features. You can see that in these later spectra here where you get these broad absorption bands of different molecules. And eventually, you end up with this dust-enshrouded remnant where it forms all this dust around it in its outflow, and it can be obscured for years to decades. So these were weird objects. We didn't know exactly what they were. There were some ideas. And then there was this Rosetta Stone event in 2008, which was published by Thailenda et al. In 2011, which was V1309 SCO. And so this is its light curves. You can see it has this nice outburst with this sort of characteristic multi-peak or peak and plateau light curve. So it looked like this class of red novae, but this precursor light that you see, where you see this little bump here, all of this scatter you see here is real photometric variability, and it turns out if you take a periodogram, this was a contact binary undergoing eclipses, and when they analyzed the periods, what they saw was that the period declined basically right up until the event went off. So this was really spectacular confirmation that this was a contact binary. The two stars spiraled in, the period declined until they finally merged. And so that's led to the interpretation of this class of outbursts as being related to either mergers in common envelope events where the two stars actually coalesce into one remnant, or a common envelope ejection where maybe they eject the envelope and don't actually merge but form a tighter binary. And so again, there's several galactic objects which are now believed to be related to this, as well as an event in M31, and now there's a whole host of more luminous events that have been found by all the ongoing optical surveys in external galaxies that appear to be related, but from more massive systems. So again, we talked about the dust-obscured remnant and the molecules that they form, but this really dominates the spectra of these events as they evolve. So they're really spectacular infrared sources. So this is an image of CK Vol, which was one of the first Western well-documented novae. So this was in 1670, and 350 years later, we're able to get optical and submillimeter imaging showing this spectacular outflow in the optical in blue, as well as, you know, the molecular emission of this sort of bipolar outflow, and then the dust-enshrouded remnant in the center. So this event, while it was, you know, thought to be a nova for a long time, is now suggested to have been related to these red novae and common envelope evolution as well. And this is sort of a typical light curve of one of the luminous red novae that may be found in an external galaxy. This one was in M31. And it has this relatively short optical outburst where it brightens spectacularly, but then quickly fades and gives way to this long-lived infrared emission that can last for years to decades. So these things really become infrared dominated as they evolve. So what kind of stars are we seeing? In a few cases, we've been able to track down the progenitors of these stars in pre-explosion imaging, either for the ones in our galaxy or with HST, typically for external stars. And we have found that they tend to live in this Hertzsprung gap part of the HR diagram. So again, these are the pre-explosion photometry of the progenitors. And this kind of makes sense. You know, the stars, one of the objects in the binary starts to evolve off the main sequence. This initiates the interaction and the common envelope evolution that leads to the final merger or common envelope ejection. But one thing that's been suggested is that we should be seeing giant stars undergo this as well, not just these Hertzsprung gap stars. And so maybe these giant stars have long periods of mass loss prior to the final merger, and they may actually obscure themselves before the transient actually happens. And in this case, you might get an infrared-only transient, and maybe won't even see this optical outburst at all. And the other, sort of things we may be missing down here, you'll notice there's nothing below about a solar mass. The lower mass stars live in binary too. Lower mass stars live in binaries as well, and are we missing some of these lower luminosity events even in the galaxy just because there's a bunch of dust from the ISM in the way? So this is where infrared surveys can really come in. So during my PhD, I was at Caltech and I worked on this survey called the Spitzer Infrared Intensive Transient Survey, where we were monitoring about 200 relatively nearby galaxies within about 20 megaparsecs in the Spitzer IRAC 3.6 and 4.5 micron bands. And this was a team led by Mansi Kozlowal and all of these people and more that I wasn't able to fit on the slide. But we identified a bunch of transients, which are kind of shown in this phase-space diagram here, the brightness of the transient in the infrared and how long the transient lasts, where you see things like supernovae and the really bright CSM interacting supernovae, things like luminous red novae here in yellow, the ones we're talking about, and some other sort of related events related to massive star outbursts. But the ones we're going to focus on, we dubbed them sprites, and these were 24 events, which, despite all of the ongoing optical surveys running concurrently, appeared to have basically no optical counterpart that was detected. So these were infrared-only transients. And the ones that are especially intriguing for this talk are these slow sprites. So these had slow, long declining light curves that lasted in excess of a year or several years, and we think may have been related to these missing common envelope events. So this is one of our objects, and this is one of the ones you're going to see the JWST data for soon. So this was Spirit's 189U, so it got this name when it went off in 2018. And this is a collection of these slow sprite light curves in the colored points, and then compared to the luminous red novae that had infrared data. And you can see they sort of have similar light curve morphologies where they brighten and then fade slowly in the infrared. This one for Spirit's 189U, this is the infrared data up here where you can see the outburst, but there was optical limits at the same time. I forget exactly whether this was ZTF or another survey, but we didn't see any optical emission during the infrared outburst. So this maybe suggested that the progenitor was already obscured or formed dust very early in its evolution and was obscured. And we were able to get a near-infrared spectra of a couple of these, including 18NU here, where we see the development of these very cool photospheric molecular features. And this, for comparison, is a well-studied luminous red nova that was discovered in the optical, as well as just some cool stars for comparison. So the second object we're going to talk about is a ZTF discovered object that had a pretty spectacular counterpart in neowise imaging, which was a pretty unprecedented low luminosity red nova. And so this was its faint progenitor here. It's in the galactic disk, so it's there's a relatively high foreground extinction, and then it had this bright infrared outburst. And you can see again, it shows some of these hallmarks, like this shorter optical outburst followed by this long-lived infrared emission. And it showed a cool photospheric spectrum and then began to become dust obscured. So we think that this could have been a merger-like transient as well, and its progenitor photometry, although it's a bit uncertain because we don't know the distance very well, seems to be about a solar mass star. But when we looked at this object in a phase space of luminous red novae, that's all of these objects up here, it was way down here in luminosity, so 10 to the 35 ergs per second compared to all of these. And if you take a model that models the emission from these events, thank you, as, well, I'm running out of time. Basically what we found was that the energetics for this event implied it had to be a really low luminosity companion, possibly a substellar companion, like a 1 to 10 Jupiter mass object. So we've gotten JWST data for both of these. And so I wanted to show off a little bit. This was our MIRI acquisition, where we had to use an offset star because we didn't know exactly how bright these objects would be to get right on them. And so we were able to put the infrared transient in the slit using this offset star. And this was the same for 18NU, although I don't have a slit verification image. This is the infrared data. So this is the NIRSpec spectrum of the ZTF object. And then this is our IFU data, because we weren't sure if we could do a good enough acquisition without the IFU for 18NU. But I'm going to focus mostly on the MIRI spectra in the last few minutes here, which we were able to get for both objects. So if we look at the actual data, maybe here in the NIRSpec spectrum, we might be seeing the warmer component of the merged remnant. But in the further infrared from MIRI LRS, we're probably seeing the dust emission. And you'll notice some diversity here. We have this broad absorption component here in Spirit's 18NU, which we think may be related to silicate absorption features. And so I just want to show this off. This is an infrared spectrum that was taken from the ground of V1309 SCO. And the match is pretty spectacular, which I think provides pretty good confirmation that this weird infrared transient we found really is related to these galactic events that we know are common envelope or mergers. And so we've done a little bit of preliminary modeling here, fitting with the dusty radiative transfer code. And you'll notice that this absorption feature is quite broad here for silicate. Normally it's around 9.7 microns, but it extends further to the red. And you can achieve this if you either use large grains or introduce another component, perhaps alumina, which adds absorption here at the redder wavelength. So, work to really nail down the composition and the mass of the dust is ongoing there. So I'll put up my conclusion slides. These are basically all the spectra of these galactic objects in this wavelength range that I could find. And so JWST is really going to blow this wide open for these types of objects because it allows us to access both objects in external galaxies, which will be much fainter, as well as the intrinsically faintest objects, which may be the mergers of stars and planets. And so thank you very much for listening, and I'll take questions.
All right, I think we have time for a couple questions. Oh, there's one all the way in the back of the room wishing I still had that box I could throw. Yeah, no, I'm not going to do that.
You mentioned that one of your objects, that ZTF thing, can be a merger of relics, right? But what is the mechanism of their suddenly get brightened? Is there lots of dust formed or what?
Sorry, could you repeat that? I couldn't hear the middle part.
Oh, sorry. Okay, so what I'm just asking is that the ZTF object, you said that this could be due to merger?
Yes, we think so.
Right. Well, but what's the real mechanism to get them, to get the object brightened in mid-IR? Is it because of a huge production of dust grain or what?
Yeah. So during the merger process, there's basically a slow and dense wind that is formed, like an ejecta, and this can form a lot of dust and molecules, so it makes it appear very red, and then as the dust forms, you get this bright mid-infrared emission.
So basically, a lot of dust formed over a very short period of time.
Yeah, and this is because in these events, typically the velocities are quite low, like tens, hundreds of kilometers per second, compared to something like a supernova. So the ejecta are very dense, and they can cool very rapidly and form dust.
All right, thank you.
Emily, do you have anything?
So in the light curves, and especially the first one you showed, like it was a historical one.
Oh, yeah.
You see this big dip just before the big outburst. So what is the mechanism of that?
That's a great question. So that is a very active topic, and I think one of the main interpretations is that this initial rise here is actually potentially due to as the two stars are merging in, you can lose mass from L2, and this can form sort of like a spiral of mass loss around the object before it actually merges. And then, as you build up enough material out there, we think it may actually obscure the object shortly before the outburst. And then also you have all of this material outside before the stars merge, and so you can get shock interactions when the ejecta go off, and that also is what helps lead to dust formation at later times. So yeah, this is all related, we think, to the mass loss prior to the actual merger.
All right, let's thank the speaker again.
Over here. Yeah.
All right, we have our next speaker is Ryan Lau. All right, go ahead.
Cool. All right, thanks everyone. I'm Ryan Lau from NSF's NOAA lab in Tucson, Arizona. I'm an assistant astronomer there, and I'm going to talk to you all today about our recent observations from our early release science program on this Wolf-Rayet star, WR140. So here's this image that we took back in July. So I'll talk about these results and also some results that we haven't shown anyone yet, so that should be pretty exciting. Okay. Oh, okay. Right. So first, what exactly is a Wolf-Rayet star? How do they form dust, and why are they interesting? So Wolf-Rayet stars are descendants of massive O stars. They're characterized by these kind of intense, extreme properties here. And so because they're so luminous, they're so hot, and they lose so much material, you wouldn't really think that they're good at forming dust. Or at least when I think of good dust-forming sources, I think of like asymptotic giant branch stars, something with very cool, dense winds. So you can form dust around Wolf-Rayet stars if you have a binary companion. So in something like this, you have an O or B star companion with winds, and then they interact with the Wolf-Rayet winds, and then you get the compression that you need to start forming dust from that Wolf-Rayet material. So typically, it's the carbon-rich Wolf-Rayet stars that are forming dust for some interesting reason. So carbon-rich Wolf-Rayet binaries can form dust if you're in the right orbital configuration through this colliding wind mechanism. So what makes them so interesting to study, to me, is that they can be, not only can they form dust, but they can be prolific dust-forming sources. So here's a study that we did of galactic WC binaries that are forming dust, and they can form up to 4 times 10 to the minus 6 solar masses a year in dust. So just for comparison, the entire dust production rate from the AGBs in the LMC is only a factor of a few more than the most intense dust-forming source in our galaxy. So very small numbers of these can have a very significant impact on the dust budget in the ISM of their host galaxies. So since these are descendants of massive O stars, they can produce a lot of dust. They evolve very rapidly as well. My interest in studying them are as potential dust factories in the local and even perhaps the early universe. So I'll skip ahead a little bit in this paper here that we put out. We did a binary population synthesis model incorporating dust production and also this dust SCD analysis. And we are claiming that these WC binaries can be an important source of carbon-rich dust at metallicities greater than about 0.5 solar metallicities. So of course, there's further questions to explore about these interesting sources of dust. Typically, the leading dust-forming sources are like supernovae and AGB stars. So there haven't been too many studies on these carbon-rich Wolf-Rayet binaries as interesting dust-forming sources. And so we've been pursuing this question with a lot of ground and space-based observations. Here's some of our papers that I've been a part of in the past year. So we've been pretty productive. And today, I'll talk about the JWST observations from our ERS program. Right, so for those of you who aren't familiar with the ERS program, just as a reminder, these are those 13 teams that are selected to attain some of the first data with JWST with the purpose of educating the community to prepare for like cycle 2 and cycle 3 proposals and to really demonstrate the key observing modes with JWST. So before I go on, I also want to advertise these posters here for dust production and ejecta from supernovae, also interesting dust-forming sources. I didn't get a chance to add Mikako Matsura's poster here, but definitely check that out. Some pretty cool images of 87A. All right, so our ERS team has about 50 people, observational astronomers, theorists, and instrumentation experts from around the world. And yeah, it's been really important, I think, working with all of these experts on dust-forming Wolf-Rayet stars and Wolf-Rayet stars, since that was really what was helpful for us in the preparation of our program and being able to get our results out so quickly and interpret what was going on. All right, so kind of to summarize the science that we tried to, the main science questions from our program, we're looking at the dust formation and chemistry around these WC stars, something that's very difficult to do from the ground and also had been difficult to do previously, like with Spitzer or other infrared space telescopes because of the small aperture size. So one of the questions that we're looking at is what exactly are the molecular precursors of this dust? What are the spectral tracers of this dust emission? We can get direct spectra with JWST observations. So to study also the dust formation, we use the aperture masking mode on NIRISS. This will be a future talk. And we use the MRS mode on the MIRI instrument. We were also interested in studying how dust evolves or if it gets destroyed at all as it's expanding into the ISM. So to do this, we were using the MIRI imager and also the MRS. All right, so one of our targets was WR140. So this really was like the perfect target for our ERS program. It's been dubbed the Rosetta Stone of colliding wind binaries because of how well studied it is. It's been known for like over 50 years. Its orbit is really well known. And there's also a lot of ground-based infrared imaging of this source where you can actually resolve the dust that's formed from the system. So this is kind of what it looks like in the reference from the Wolf-Rayet star. So what happens is in this 8-year eccentric orbit, you get dust formation every time the O star approaches the WC star here. So in this red region of the orbit, you get dust formation for about a couple months in this like 8-year period. So what we're looking at here, this is an image that we took with COMEX, which is a mid-infrared camera on Subaru, of the last dust formation event, which was in early 2017. So this was taken in 2020 here. So this really was this ideal source for investigating this, for pursuing this program with JWST, because this also gives us an idea of what the spatial resolution of we expected. So I just want to point out this image a little bit more because this is taken from like an 8-meter class telescope on Mauna Kea, like one of the best sites to do infrared astronomy on the world, so especially at 12 microns. So this is one of the best images at this wavelength that we had of this system until we got the JWST observations. So we saw this and we're like, oh no, something broke, or like, I don't know what's going on, or it's too bright. But then like we looked at it a little more closely and we're like, oh wait, we recognize this structure here. These are these dust shells, but we don't just see one, we see over 17 of them just stacked up, evenly spaced over 130 years of past dust production from this system here. So we saw it, it's like, okay, that's probably what's going on, but we need to really understand what's real and what's not real. So there was a really good comments from one of our referee reports that we should try to overlay the PSF on it just to make sure that we know what's real and what's not. So here's the 15 micron Miri filter PSF from WebPSF. And we, as we expected, this stuff here, these 8 diffraction spikes are diffraction spikes. So these are artifacts. But that means that all this other stuff should be real, or it must be real, including this like weird linear feature here that's like cutting through. So this has to be a real feature. It's not a diffraction spike. All right, so that's pretty cool. Like we know, we think this is real, but when you have something that looks this amazing, you want a model to be able to really demonstrate that we understand what's going on. So maybe serendipitously, but sort of not to, I've been working with this team at University of Sydney who have been studying decades of high-resolution infrared imaging observations of W140. And they published this paper in Nature, so it was led by Yinwo Han, who's a grad student now at University of Cambridge. And he produced this geometric dust model of what this dust shell should look like every time you get dust formation around this system. So we asked Yinwo, well, what happens if you take 20 of these and you stack it together? And we saw something that just looks exactly like our observations. We were just super blown away, like this doesn't typically happen where you have something that looks like exactly what we see. Even this structure here is reproduced, this like spear-shaped thing, and so that's just the enhanced emission that you get, or due to column density enhancements along this line of sight from these spiral shells there. Yeah, it was pretty crazy. Okay, oh yeah, the other thing I wanted to point out too is we have these awesome 3D prints here. So this really helps you, I guess, visualize what is going on in the system. So we've been collaborating with Carol Christian here at Space Telescope and Tom Madura to develop these 3D models. So you can kind of, it's easier to visualize it this way, I think. And also these like 3D tactile prints to use as like education or outreach tools for students with blindness and visual impairment. So yeah, we've been working on that too, which has been pretty nice. Okay, so that was kind of half of our science. The other thing we wanted to do is, as I mentioned, get spectroscopy. So we have MRS observations of this as well. This is sort of, you can recognize the dust feature or the dust arc here. And we were looking at what exactly the spectral signatures are of this dust. So we got this nice spectra of exactly what we wanted to see. We saw these broad emission lines here at 6.4 and 7.7 microns that are associated with unidentified infrared bands or polycyclic aromatic hydrocarbons, which we heard about this morning in Jessica Sutter's talk. So we know why these are interesting. And now that we see this imaging observation of dust that's surviving out into at least, let's see, 17 shells, we know what this dust is composed of. We're claiming that these dust-forming WC binaries are enriching the ISM with this carbon-rich aromatic compounds and also carbonaceous dust. So the question of where pHs could come from, these could be important sources since you form them very quickly, and you also see these pH features in the early universe. Okay, so the very last minute or two of my talk, I wanted to, this is the really interesting, crazy stuff that we saw that we haven't talked about yet. So we're looking at our MRS data around this particular emission line, this sulfur 4 10.5 micron. And if you look closely here, we're looking at different velocity slices, and there's a little ripple that kind of propagates this in this direction. We're super confused as to what this was. We thought it was like something weird going on, but in working with the MRS team, they were convinced that this is real, and so we're like, okay, this must be real. So what we did is we used JDA-Viz and CubeViz with a lot of help from Ori Fox to do a continuum subtraction of the dust to get rid of all that. And we see this beautiful emission structure traced out by the sulfur 4 emission line. So we're actually looking at the colliding wind structure, not just where the dust is, but of this entire structure mapped out in this 3D velocity space. And of course, you need a model to be convinced of this. These are SPH hydrosim models led by Christopher Russell, who's a postdoc at University of Delaware. And if you just look at this, you see the match between the hydrosim models and the MRS observations. So it's like we have a pretty good idea. We think we're doing this 3D mapping of the colliding wind structure around a massive star, which I'm not sure if this has been done before. And so we didn't expect to do this was possible at all. So I think this is like really opening up doors with what JWST can do for not just colliding wind binaries, but for massive stars to map out this 3D structure of ionized gas. Yep, so that publication is in prep by Christopher Russell. And I'll just end on this slide, so a summary of the results from this paper we published in Nature Astronomy a couple months ago. So thanks.
Right, do we have any questions?
Brittany Miles, University of Arizona. Thank you for an accessible talk. I was curious where you extracted the spectrum of the PAHs, and do you see changes in specific lines if you extract over different areas?
Yeah, that's what we wanted to do. So we did just this region here, but we wanted to look at a comparison between this region here and this here to see if they're exactly what you said, like to see if there's any changes in the pH features as a function of time and also a function of temperature, since these dust grains are cooler than the dust here. We didn't get to do that in this paper because this is still kind of close to the central binary, so we're worried about any kind of contamination from the central star that's influencing the emission that we would detect here from this first dust arc. Also, we had this extended ionized gas emission that we hadn't anticipated, so we're taking our time to do that particular study, but that's exactly what we want to do next.
There's a question of whether these are Miri MRS observations, real quick.
Yeah, these are MRS. Yeah, the spectrum is from the MRS, the continuum subtracted MRS spectrum of this feature.
Okay, Emily, do you have a question online?
There are 3 questions online. So Chick Woodward says, how were you able to observe this source of Miri successfully without saturation, as the JWST ETC would suggest? With 40 groups, one assumes the central pixels are saturated.
Yes, so we spent a lot of time using the ETC and talking to a lot of people about saturation. So this is saturated here in the core, and even part of this first dust shell is saturated in the Miri imager observations. So that's why the MRS observations are so helpful, because they're not saturated. You're dispersing light in the spectra, so we don't need to worry about saturation in this region. And so perfectly complements the imaging observations, so you can get detections of the entire thing. So yeah, we spent a lot of time really making sure that works.
In the interest of getting back on time, could you have those questions put into Slack, and then maybe Ryan be willing to answer them there?
Sure.
So let's thank our speaker again.
Thank you.
Can you all hear me? All right. It's PowerPoint. It does? Okay, good. Even better then. Yeah. Oh, excellent.
Let us welcome our next speaker, Margaret Meissner.
All right, thank you, Susan. All right, well, anyway, I want to thank everyone on the JWST project. I'm going to say particularly the engineers who actually got this amazing thing working for enabling these spectacular observations. I am thrilled to talk to you about the ring and the ejecta of the iconic Supernova 1987A with the MIRI MRS spectrum. A quiz for you all. You have to figure out and guess what wavelength I'm showing of 87 on that. The answer will be later in the talk, but think about what you think that is. The work I'm going to show you is really on behalf of a united US and European MIRI EC consortium team that are listed here on the right. And let's get on with the results. So to orient you to what I'm going to show you, I want to show you some recent wide field camera 3 images by Larson, one of our team members, to orient you to the structures. So on the left is the entire structure of Supernova 1987A. The outer rings are basically rims, a bipolar nebula thought to be created in the progenitor wind, thought to be created by a binary merger. And then the ring itself, of course, is the progenitor wind as well. On the right-hand side, you zoom in, and at the center is the ejecta, which is basically the exploded remnants of the central star. And this ejecta is colliding into the progenitor wind, and that's why you have a shocked ring emission. So the ring is shocked, and then it's gone out so far that now we're getting a reverse shock coming back towards the ejecta. It hasn't hit the ejecta, but it's coming back. Now, Supernova 1987A was observed in July, and we had sort of a pretty intensive campaign. We observed it with the MIRI subarray imager, the MIRI MRS, that's what I'll be mostly talking about, the near spec IFU, and then as freebies you get MIRI simultaneous imaging observations when you observe with the MIRI MRS. Oops. There we go. And you get near-camp parallels of some nearby nice star formation regions when you observe with the MIRI imager. Now, the parallels I'm not going to talk about. That's actually a star formation study, but I am going to talk to you about 87A. So just to give you a little more context, Spitzer IRS observations were done over the course of its mission, and in this 2010 paper by Dweck, you can see that as time went on, you increased the intensity over time. And then when you look at the features, they're dominated by these silicate features at around 10 and 20 micron. And then you see a handful of spectral lines. And what we see with MIRI MRS, and this is of the entire cube summed together, just to show you that spectrum, we again see this dominant structure of the silicate features here. And then we see many, many spectral lines. And we see many more spectral lines because the spectral resolution of the MIRI MRS is about a factor of 10 higher than the Spitzer IRS. So you get that nice line to continue contrast, and you can pick out these lines. So as with Spitzer, we see these neon 2 and 3 lines and these argon lines. But in addition, we see neon 5, neon 6, hydrogen recombination lines. And then we're able to separate the oxygen 4 and the iron line because of the spectral resolution of Spitzer. And so we can actually see this very broad iron line and sort of this narrow iron 4, oxygen 4. All right, now in addition, so with Spitzer IRS spectra, people kind of surmised where the line was coming from by the width of the line. If it was really broad, like the iron line, it came from the ejecta because it was exploding. If it was narrow, it must be coming from the ring. But with MIRI MRS, you can actually see visually where it comes from. And so I'm just going to show you a few of these spectral lines. So here we have neon 6. So these are one of the newly uncovered spectral lines. You can see it's coming from the ring, but then you have this diffuse outer part here. And this is likely maybe, we haven't finished studies of it, but probably, you know, spatially coincident with the reverse shock region. And then you have neon 2, 12.8 microns, and you see it from the ring and the outer rings. And then neon 3, like neon 2, you see from the central equatorial ring and then the outer rings. And the answer to the quiz was neon 2, 12.8. How many people got it right? All right, now argon, on the other hand, the 6.99 micron feature, is enhanced in the ring, but also in the ejecta. And this was surprising because when you look at the Spitzer IR spectrum, it's narrow. And so people said, okay, this comes from the ring. I mean, that's the, so this is, so when you look at this, you can see that it's brightest at minus 234 kilometers per second, and it's coincident with purported compact object at the center. So that was sort of a revelation that MIRI has provided us. And as we know from our near-spec IFU, iron comes from the ejecta, from the center. And so there's a poster by Beth Sargent, and there's a paper in prep by Josephine Larson on this. But on the left, we have basically a 3D rendering of the iron line emission. And this gray elliptical is the equatorial ring. And this is basically composed from, or derived from, all these beautiful channel maps. And we show the channel maps here in addition because these equatorial rings, but you can see there are these hot spots here where you're seeing the ejecta hit the equatorial ring. So go see the poster by Beth Sargent. And we use that to look at the origin for the iron 26 micron line, the really broad feature that we saw in the MIRI MRS. And we can see that it's exactly the same as what we're seeing with the near-spec line profiles. And then here is this oxygen 4 line, which we'll have to get the spatial deconvolution because things get very fuzzy when you get out to the long wavelengths with MIRI MRS. All right, now what about the dust emission? So MIRI MRS, again, was dominated by silicate dust. So I'm showing you the image from 10 microns and 20 microns, which centers at the peaks of these silicate dust features. And you can see that it is dominated by the ring emission. In fact, if you do a spaxel on the equatorial ring to say, okay, what is the spectrum of that, you can see the dominance of the silicate features, and then you can also see these line emissions again. So it's silicate dust, and then with the MIRI imager, we imaged it in 4 filters of the 5.6, 10 microns, 18, and 25.5. And what we are showing here is in the green contours is that line emission from the argon, which highlights the ring and the ejecta at the center, just to kind of to guide your eye. You can see with the imager, you get higher quality images than you do with MRS, so it's worthwhile using the imager. I think we also saw that in Ryan's talk. With the imager, you get these very crisp features. And you can see as you go from 5.6 to 25, the dominant, you still see the ring structure. You see that it's brighter on the west compared to the east. But then you also see that as you go to the longer wavelengths, the resolution degrades. And whether or not there's a real difference in the width is still being investigated. But in general, most of this wideness and sort of more diffuse emission outside may be dominated by just the PSF. Now, we also, just to try to investigate whether there are differences, we did an overlay of the imager. So in each of these 3 images, the color scale is the 10 micron image. And then overlaid is the contour of, this is the 5.6 in the green contour, and you can see the 2 stars that are nearby. And then this is 18 microns in contours, and you can pretty much just see the ring. And then down on the bottom here, again, the green contours, you can see that it goes further out. So to figure out some more investigation of the dust, we've made temperature maps. So on the left is a simple black body model, and on the right is the silicate model, and we've overlaid this, the 5.6 micron image, as a guide to your eye. The black body model uses all the filters, and the silicate model fits to all but the 5.6. And you can see that the west, again, is brighter than the east, so there's this temperature gradient across on both images. All right, so I'm just going to let you know when you can expect to see things released in more complete form. We have a near-spec IFU overview paper that's in prep, planned to be submitted before the holidays. Patrice Bouchette's preparing one of the Miri Imager, and then we have one combining near-spec IFU and MRS on the argon measurements by Klaus Franzen, and then the Miri MRS overview paper, which is a lot of what I've discussed, is in prep by Libby Jones. And we are going to continue with these 87A observations. This is just to show you the time evolution that happened with Hubble. This is a time-evolving object, and we plan to continue monitoring it with 87A. So we are putting remainder of my GTO time on this to go back and do MRS again to get a second epoch of observations in order to get more MRS spectroscopy and a dedicated background image. And then the goal is to look for flux variability, spatial structure differences, and then extra signal to pick out any weak features. So that's it. I'm open to questions. Thank you. Leave it on this.
A couple of questions in the room, so I'll start here.
Hello, thank you. Great talk. I'm wondering if you have a limit on the dust mass in the equatorial ring. In the equatorial ring.
In the equatorial ring? Not yet, but that will be part of the paper.
Sometimes, because of bright stuff outside, you cannot see really ejecta dust, but I see still the flux is 25 microjansky, so you might want to zoom in and see. So do you have a spectrum for central part?
Yes, no. I mean, that, of course, is one of the things I'm very keen about. It is a challenge. So we will have to do a lot more work on the data and the modeling to get down to the level with confidence. It's not clear.
Yeah, so you can
see something at the center.
You extract the flux and the center only, it's really still quite, bright at the center.
It is. That's the imager, and if you just go back to the MRS, it's. I think you have to understand the instrument at a better level than we do currently to start pushing it down to that. But it is one of the goals.
Okay. Do you see any CO fundamental lines or fundamental features? CO features?
Not in the whole spectrum, and we don't. We don't. Not
obvious.
Yeah.
Okay. Thank you.
Do you have any questions online, Emily? All right, let's thank our speaker again for that wonderful talk.
You're online next.
Oh, it's on. Okay. Our next speaker is online, so I'm going to stop sharing. So is our speaker online? Wesson?
Yes, can you hear me?
There we go.
Can you hear me?
Had you
Am
for
I
a
audible?
moment. I think I heard you speak again, Roger.
Am I there? Testing.
So I can't see your slides. You still need to share your desktop and then.
Yeah. A second.
And then can we get the volume up in the auditorium, please? Okay.
Okay, do you see my slides?
No, we see the share screen button window.
1 second.
Try sharing again. Okay, now we see slides, so you just need to make it full screen mode. Yes, that looks good. And can you speak again so we can check the volume?
Yes, how's that? Am I audible?
Yes, everybody's okay with that? If we could have one more notch in the auditorium. Perfect, okay. All right, next we have Roger Wesson from Cardiff. Go ahead.
Okay, thank you very much. Sorry for those slight technical hitches at the start. It's a real pleasure to be able to talk at this conference and to see all the wonderful results that everyone else is sharing, and to share the work that I've been a part of on the Ring Nebula, which I'm presenting on behalf of this team. My colleagues are listed on this slide, a team from Europe, North America and South America. And yeah, so the work we're doing is on JWST imaging and spectroscopy of the Ring Nebula. I hope my slide has advanced successfully. Shout if it hasn't. So I'll tell you about the Ring Nebula briefly. It's a planetary nebula, and planetary nebula is the end stage of the evolution of low to intermediate mass stars, up to about 8 times the mass of the Sun. These stars, after they've finished burning hydrogen and helium in the core, continue helium burning in a shell which becomes thermally unstable. It kicks off the outer envelope of the star, reveals the hot core, and lights up these ephemeral and beautiful phenomena, planetary nebulae. The Ring being quite a iconic example of the planetary nebula phenomenon. It's a little under 800 parsecs away. It's been observed by several previous space missions. The images on this slide, they're not to the same scale, but just to show you what some of the previous space telescopes have seen. On the left is a Hubble Heritage image showing the bright ionized inner regions of the Ring Nebula, which I think you can probably just about see. There are dark clumps silhouetted against the bright ionized material. I'll talk more about those shortly. And on the right is the Spitzer Space Telescope image, which shows you the bright ionized ring in the center of that large outflow, and it reveals the molecular material, cool molecular material at much greater distances from the central star, tracing the much older episodes of mass loss. So our team has obtained 19 hours of JWST time. We've obtained images of the Ring in 4 near-cam filters and 9 Miri filters, covering, centered on mainly the bright inner main ring of the nebula, but also covering some of the faint outer molecular halo. This 3-color composite here shows you some of the components that we're interested in looking at. The aims of the program really is to map the different components, atoms, ions, molecules, and dust, and to understand what's going on in this environment that provides an astrophysical laboratory of sorts. It's got a relatively well-defined geometry. It's got a single hot source at the center, and we want to study the interplay of the radiation and the stellar winds with the material in the Ring, and see how molecules form, evolve, and survive in this environment. So in this three-color image, blue light is oxygen 4. That's predominantly emitted inside the main ring. Red is hydrogen, coming from mainly from the clumpy ring, and green shows you the molecular hydrogen emission that's coming from the outer parts of the nebula. So there's obviously a wealth of structure in this image. It's spectacular detail, and you can see, for example, all of the radial features that are likely starlight illuminating the material beyond the ring through gaps in the clumpy ring. So our spectroscopic observations, we've observed two particular regions with both near-spec and NIRI. These regions are shown on this slide. The north region is within the main clumpy ring, and the west region on the right-hand side is slightly interior to that, in what should be a harsher environment embedded within the ionized gas. So just to show these regions in a little more detail, well, the west region in a little more detail, on the left panel here is a Hubble image in H-alpha, which shows you the knot silhouetted against the background radiation. And on the right is a NIRCam 2.12 microns H2 image. So you can see that the knot is bright in molecular H2, and there's also a lot of H2 emission coming from the surrounding field. So the spectra are incredibly rich. This is the whole near-spec region in which there are hundreds of spectral lines. The marks below the spectrum on this slide show you, well, in orange, marks indicate the position, well, the lines indicate the positions of all the spectral lines that we've measured and identified. The orange lines correspond to H2 lines, molecular hydrogen, and the black lines correspond to lines from other species. That's mostly ionized hydrogen, ionized helium, and a few heavy elements, collision excited lines. But yeah, so these spectra at these wavelengths are really dominated by the row vibrational lines of molecular hydrogen, of which we detect about 200 in the north region and about 150 in the west. I'll mention that these spectra, we're looking forward to updated calibration files, because we had to apply some arbitrary scalings to get the different bands to more or less line up. So we look forward to updated calibrations to do an even better job of measuring and identifying these very faint emission lines. So to measure and identify these lines, we're using code alpha, automated line fitting algorithm. This is a code that I originally developed to look at. It was intended to work on spectra regardless of wavelength, but it was originally optimized for optical spectra. So I've done some work, and with assistance from the team, on updating it and optimizing it to fit JWST spectra. I think it's doing a pretty nice job. It just takes a few seconds to go through the whole near-spec spectrum and fit all of the hundreds of emission lines and provide identifications of them. So yeah, on this plot, I think it's testament to the beautiful quality of the data. The data itself is in purple, and the fit is overlaid in blue. You can hardly see the purple underneath. So the data is really well characterized by the fits we're putting on top of it. Once again, yeah, orange lines here correspond to the molecular hydrogen. So this is just to show the MRS spectrum, not quite as densely packed with lines as the near spec, but again, measured and identified with my code alpha. Which, if you're interested in using it, it's all publicly available, and if anyone is interested to use it and needs assistance, I'm happy to try and get it working optimally. So from these hundreds of H2 emission lines, we do some simple calculations, assuming LTE, calculate the level populations from the line fluxes to produce these excitation diagrams for the north and the west knots. And these show that this simple assumed LTE model at a single temperature is quite a good representation of what's going on. It implies a temperature of about 2,900 Kelvin in both regions and very similar between the two regions. The color coding on this corresponds to different vibrational upper quantum numbers in the transitions, and it's up to vibrational quantum number nu equals 7, visible as the blue triangle at the far right hand side in the north. But yeah, we've got a lot of lines from transitions up to nu equals 5 and a handful at higher excitation still. So that's also consistent, just to show you some of the spatially resolved near-spec data, which shows that this knot in the west is heated by shocks to molecular hydrogen. On the left here is the 2.12 micron slice of the near-spec field. The green crude arrow there points towards the central star, just to show where that is. And on the right-hand side is the sulfur-3 0.9 microns line, against which the knot is silhouetted. And it's from that image that the black contours are made. And yeah, the H2 emission is clearly coming from this dark knot. And in the middle is neutral carbon emission, which traces shocked gas. And that shows you that it's there's quite bright neutral carbon emission right at the head of the knot there, supporting the idea that this is heated by shock interaction with the outflowing stellar wind. So I'll end with that. I'll leave you with my summary slide on which I've just got a few of our separate images to illustrate the top what beautiful data, what beautiful images we have. And I'll be glad to take any questions.
Thank you for that lovely talk. Do we have any questions online first? No? Do we have any in the room? Okay.
So your H2 excitation diagrams seem to be show some extra component might be existed at high temperature, and that's one question. Can you characterize that emission? Also, do you see H2 emission different imaging, at different lines? So I mean, some other object I see different structures from the different H2 lines. So you see over there some more additional components there. Will be very interesting if you can make a to track down where the difference come from in the imaging.
Yes, particularly in the north, at the high excitation lines, you see that there's some upward curving of the level populations that might suggest there's some material at higher temperatures. I would say I'm cautious about that. I'd like to wait for the updated calibrations, flux calibrations, and remeasure everything and see if that upward curve still remains.
It looks like we have a question online.
Yeah, a question from, excuse me, a question from Joel Kastner says, seems the shock origin for the H2 emission is now settled. Is UV excitation still a possibility? Is the TEX, I guess the temperature, so high that one might expect dissociation?
Sorry, could you repeat that? I didn't quite catch some of that.
Yeah, seems the shock origin for the H2 emission is now settled. Is UV excitation still a possibility? Is the TEX so high that one might expect dissociation?
Right. Well, yeah. I mean, it does. It seems like it's shock excitation is really all you need. I should say that we have some preliminary cloudy models that we're also developing that also support that interpretation. There's no need for another source of heating to reproduce these excitation diagrams. They also show actually that the density in the north is quite a bit higher than the density in the west, and they're both quite high density regions, but the west density is lower. So the fact that we see rather fewer lines in the west seems mainly to be just that there's less material there, rather than any great differences in physical conditions between the two regions.
Okay, with that, let's thank the speaker again. As we break here, I have a couple announcements. I want to remind you again that we're going to try to take a conference picture in the coffee break after the next session. We'll try to get even some of the online people, so if they're willing to turn their cameras on, we can get them on screens here in the auditorium so we get everybody. We are coming back at 1:15. I've gotten nods that is correct, so that's where we want to be. And then I have a list of names that need to go talk to the registration desk. So I'm going to read off a whole bunch of last names. If you're one of them, please go talk to the kind ladies up at the front. I promise you're not in trouble. Bonaventura, Peng, Rathke, that's Alexander Rathke, Pablo Ovalle, Jonathan Tan, David Filker, Alex Chung, Matthew DeFuro, Stephen Gilman, Remy Indebetua, Daniel Lengarudi, Takahiro Morishita, Benjamin Rackham, and Isang Yoon, and I apologize for any names that I butchered. You're free to go.